All right. Well, hey, everybody. Thanks for tuning in today. We're going to get through this presentation. We're going to have a couple of breaks mixed in, and so you don't have to sit through the whole thing. And uh, we're going to do it a little ad lib, and we may hand off between myself, Lee, and David Eoff. And so we'll just see how that goes. If you have questions, go ahead and put them in the chat, and we'll try and monitor that and communicate with each other to answer any questions that come up. We should also have some time at the end to answer questions. This may not quite go to 3 hours. We'll see. It depends on the questions and everything. So we'll go ahead and
David Eoff. I'm the co-presenter, and you can tell Lee has a deep voice. My son says I sound like Kermit the Frog over the computer, so that's how you'll know.
All right, so let's go ahead and get going. If you guys have any questions or anything afterwards, also our email addresses are there. You can also get our contact information off the website and get in touch with any of us. We have other offices, of course, scattered around the country, depending on what region of the country you're from. If you call the main number, they'll make sure you get to the right people. But if there's anything that you'd like to ask us directly, those are our email addresses.
All right. I wanted to thank everybody for attending. You know, it's super brave to sign up to attend a 3-hour webinar. And, you know, in the before times, we used to come to your office and do a lunch and learn and provide you a nice lunch. Now we just live stream a PowerPoint presentation because of the COVID. In fact, anytime now you get crummy customer service, it's because of the COVID. Somehow it's safe for a flight attendant to bring me a water, but it's unsafe to bring me a cocktail because of the COVID. So I'm sorry we're not in your office and we didn't provide a nice lunch, but thank you very much for attending this. So thanks, Lee. Can you get us going?
Yeah, and I just want to mention one more thing too. If for some reason you'd like to have this particular presentation given live to your group at another time, that's certainly possible, or our regular 1 hour presentation, we can do that live with you. Michael may still be muted or stepped away, but I believe the case. So
sorry, Lee. Sorry, you dropped out. What was your question?
Oh, this is going to be recorded and available online as well. Is that correct?
Right. Yeah. Anyone that would like this this presentation can contact us. They can contact us. It will be posted on our YouTube channel for future viewing as well. And if you have questions from that, you can also just email us via the emails below. But yeah, we will post this on our YouTube channel.
Great. See, we made Michael talk after all during the presentation. Okay, so we're going to get moving here. Again, that's our information. This is just kind of what you're going to see when we're on a break, which we're not going to have yet. It's a little early to have a 5-minute presentation. So this is actually something that's available, and we're offering it to everybody. We'll send it out to you for attending the webinar. If you'd like to have it, just go ahead and email Michael Sipes on the right-hand side there. And it's a anytime as well to answer any questions there. But this is a nice little reference guide that Preferred put together for engineers. So again, if you'd like a copy, just contact us. I think we did a pretty complete introduction there, but those are our email addresses again and our cell numbers, or at least mine. And again, ask any questions anytime and give us a ring, hopefully after 3 hours. So the main sections that we're going to go through here, the first one is starting conceptual design. You've got a new project, maybe a clean sheet. So we're going to go through that, kind of go through some of the questions that need to be asked up front, helpful information that would be good for us to have early on. After we have some of that information, section 2 will bring us into what we do when we have that base information and we need to start doing some capacity and equipment, some capacity calculations, decide some of the major components ahead of time. Is this going to be underground and above ground, that kind of thing. Section 3 goes deeper into those components. Specifically, what do we want to use, which pump model. Now we know what pump type, for example, or underground or above ground tanks. Now we're going to get into, in section 3, actually selecting those major components, the right size, etc. And section 4 just goes into a lot of different design considerations, so including specifications, certain things like temperature controlling, different environments, hot environments, cold environments, etc. So it's a kind of a lot of miscellaneous mishmash of different things to keep in mind during this whole process.
Lee's microphone keeps cutting out every once in a while. Until we get this fixed, I'll try and cover for him. We're going to do a few slides.
What's that? Oh, I'm sorry. Can you guys hear me?
I can. Every once in a while you're cutting out. I get a little bit of a garbled kind of a sound, and then you go quiet for about 10 seconds.
Yeah, I noticed a little flash on my screen that said reconnecting to audio. So I don't know, maybe I never have internet problems, but maybe I'm having one today, of course, of all times. But just let me know if it, I'll try and keep an eye on that and make sure. So where we begin is starting with these beginning questions. So basically, what are the electrical requirements? That usually where it starts is, hey, we need this, we have this electrical load need at this site. That's kind of what we start with. What are we dealing with as far as generators? And then also, what kind of runtime requirement do we have? Is it 24 hours, 72 hours, 2 weeks, 10 days, whatever it is? Next thing also, especially in the case of a data center, specifically what are the redundancy requirements? Do we have 8 generators, but we only need 5, 3 are spares? Or do we have a 2N or a 2N plus 1 situation? So we're going to ask those questions too, because that'll affect our fuel load and how we're moving the fuel around. Of course, the next, one of the other things is above ground versus underground. What do we have room for? What is the owner requirements? Are we buried in a parking lot? Do we have a tank farm area, somewhere in an outlying area where we've got plenty of room? And of course, also component locations. Are the generators indoors? Are the day tanks indoors? Are they outdoors? Are they in a CMU yard, for example, etc.? So those are going to be the sort of the base level requirements that we're going to start looking at so that we get a sort of a base level of knowledge about what we're dealing with. Getting a little bit deeper into that, we wanted more information about the generators. So how much power is needed for the emergency generator system? In other words, is it a 6 megawatt system, that kind of thing? How's that broken out? How many generators do we have and what size are they? Do the generators have belly tanks? Do they have separate day tanks? Combination of both, etc. And of course, also what we like to know as soon as possible up front is, do you have a copy of the generator submittal? A lot of times from the electrical engineers. If so, can we see it? Because we can get the actual consumption numbers off of that information. And a very valuable piece of information in the submittal copy a lot of times is information about the belly tank. Belly tanks are becoming more and more and more popular, and we'd like to see the actual belly tank drawing if possible, because that tells us how deep the belly tank is. So in other words, what kind of sensors we can use, how big the bungs are, how many extra bungs there are, etc. So the earlier the possible on the generator submittal actually is quite valuable. So we usually are going to ask you for that up front. Next thing being the runtime requirement. Basically, how long do we need to run the system? Life safety is I'm sure most of you know, is usually about 8 hours minimum. Hospitals are generally these days going to be 72 hours. Data centers usually, I mean, we've seen 24 hours, we've seen 72 hours. I would say a lot of the ones we're working on these days are at least 72 hours. We've worked on ones that have been 10 to 14 days. So it really depends. Actually working on a project right now that has not been design complete yet, but we're looking at running generators for multiple months. And
in Florida now, nursing homes are required to have 120 hours of fuel storage. So it really just depends on where you're at in the country or where the facility is at.
Yeah. Depending, fuel trucks may or may not be running. I mean, what we're trying to say there is, it looks like I may have cut out there, so I apologize if that happened. Depending on the scenario, say a natural disaster, like an earthquake, you know, it pays to be cautionary to that kind of situation, because you know, you may have a response contract with a fuel supplier that says, yeah, you know, we're going on contract and we'll be out there within 72 hours to refill your tanks. Well, a lot of that can change.
Yeah, it depends on what the natural disaster is. Like they're having a snowstorm in the Northeast right now, but the fuel trucks will generally be running in a snowstorm. However, get an ice storm, especially in the South, and the fuel trucks may not be running. And there were two recent events, you know, somewhat recent. During Hurricane Katrina, the roads into New Orleans were down, so they couldn't get fuel trucks into New Orleans. And then after Hurricane Maria in Puerto Rico, there were a lot of down trees and down power lines on the road. So it took a couple of days for the fuel trucks to get running again in Puerto Rico, or if you were anywhere outside of like San Juan. So you need to think about the type of disaster, or the type of event that you're designing for, and how much fuel, and that impacts on how much fuel you store at the site.
Yeah, it could be any conditions like that, like roads blocked or ice storms or bridges are down because of an earthquake or anything like that. And it could be that the fuel delivery company is up and running, but they just physically can't get to your location. So that could happen. So we get into redundancy at this point. Most projects have at least one redundant generator. That's going to be, you know, hospitals, data centers, that sort of thing. If it's a smaller site, maybe not, but most of the larger commercial sites that we work on have redundant generators or have failover generators. So one thing that does come into play here, especially when we're doing things like calculating how much fuel is necessary, total load for the site, we may be asked to, let's say you need 5 generators to run the site, but you've got 8 total. We may get into a situation where, hey, you know, those 3 are just failover generators. So I need to calculate my total fuel load based on 5 generators running at full load, rather than 8. So we're going to want to have that discussion as well. It may be also that you run 6 of them at 70%, you know, 75% load, that kind of thing. So we're going to have that discussion as well and sort of establish what our baseline total fuel requirement for the site is and adjust things accordingly. As far as hospitals and that sort of thing go, usually the boiler fuel is separate, but we're going to keep that in mind as well. Also, there's a really good white paper, especially if you're working on a data center project, and I'm sure some of you are familiar with this. It's called Tier Classifications to Find Site Infrastructure Performance. It's a really good paper that will explain the differences between the tier requirements, like, you know, tier 2, tier 3, tier 4, if I can speak, and you know, n+2 to n+1, etc. So that's a really good reference document, and it gets into a lot of detail, but it's not a terribly, you know, it's not a book. It's really a white paper, so it's very worthwhile to take a look at if you've never seen it. I apologize for that. My mouse is a little bit sensitive. I won't use that anymore. The next thing we're going to really look at is above ground versus underground tanks. And as you can see left and right, there are advantages and disadvantages of both. It really is just which one is more appropriate, but above ground generally is simpler, it's less expensive, it's a little bit quicker. It's obviously less disruptive to the site as far as excavation, that sort of thing goes. They're generally not going to be any significant thermal issues, but it could happen in really extreme climates. Part of the limitation here is limited capacity. You can get approval to do much larger than 48,000 gallons, but generally 48,000 gallons aggregate is the limit. And we have run into sites in the past where neighboring sites, such as residential areas that have two-story houses that can see over fences, like at VA hospitals and stuff, we've run into situations where people have been sensitive to having exposed fuel tanks, and so, you know, that might be a reason to move to an underground tank as well. Underground, obviously, a lot more complex, more expensive. The complexity in California in particular is quite a bit different. We have AB 2041, LG 113, a lot of different codes and everything that need to be followed, and obviously very different equipment. They're also, you know, a little bit more difficult to inspect. Maintenance requires certified inspections by certified individuals, etc. They're generally a little bit harder to expand. So if it's a modular growth type of thing, above ground's a little easier. Obviously also more regulations, and the advantages though is that you have virtually unlimited capacity. They are hidden, and the tanks and piping are more insulated from extreme environments. So again, it's just really going to be what is more appropriate for your particular project.
Lee, isn't it true in a lot of cases the decision of above ground or underground storage tank has already been made by the time the project gets to the engineer?
I would say probably most of the time, but in some cases not so much, especially if it's a remote site that's, say, a new data center. Sometimes there's some flexibility there, but we've also switched from above ground to underground or vice versa in, you know, densely populated, you know, like downtown areas where it ends up just not working. We just can't do it for some reason. We can't excavate that particular sidewalk, or we can't block the street, something like that. So yeah, I mean, generally I'd say it's usually mostly decided ahead of time, but sometimes it switches up. Has that been your experience a little bit here and there?
It seems like I do more hospital projects than data centers, and it's usually the architects that decide early on in the project where the main tanks are going to go.
Yeah, for sure.
And I found if people complain that the main tanks are ugly, sometimes they'll put the logo of a local sports team on the side of the tank, and then people consider them to be less ugly.
Yeah, we've had a couple of VA sites that have put decals and painted the entire tanks and made them look pretty nice. So yeah. So above ground tanks, there are two basic types, UL 142 and UL 2085. UL 2085 tanks are UL 142, by the way. It's just a little bit more. So UL 142 is steel, sometimes open secondary, rupture basin type tanks, sometimes closed top. UL 2085, on the other hand, is double walled, closed top, fire rated or vaulted tanks.
I think they're usually 2 hours.
Yeah, 2-hour rating.
And UL 2085 tanks are typically for above ground, and we can supply UL 2085 day tanks, and we partner with suppliers that can do UL 2085 main tanks as well.
Yeah, Dave, you're a little muffled. Day tanks are generally UL 142 because they're smaller, usually indoors or often indoors. A good rule of thumb here is UL 142 is generally going to be up to 660 gallons, usually used as day tanks. When you go over 660 gallons, you're usually looking at UL 2085. And also if you've, if you're exceeding that capacity and it's within a building, they're usually going to require UL 2085 as well. So a good rule of thumb is day tank under 660 gallons, or even a main tank under 660 gallons, UL 142 is okay. Once you go above that, in most cases, it's going to be UL 2085, protected class tank. And I'm going to kind of try and go a little bit quicker. So if I'm going too fast, let me know. Underground storage tanks are going to be double wall these days, either fiberglass double wall or composite, which is a steel primary and fiberglass secondary. Pressure systems, some states, like California as an example, where I am, require continuous monitoring systems for tanks and underground piping. So that's the pipe interstitial as well as the tank interstitial. Fiberglass tanks are going to be monitored generally by brine or polyglycol, and composite tanks are usually going to be continuously vacuum monitored. The piping in the state of California, for example, the secondary will be continuously vacuum monitored in most cases. As far as sumps go, in California, everything needs to be double walled if it is a pressure type system. So in other words, you've got pumps in the tank that are pushing the fuel out. In other systems that are suction, if we have a length of pipe that's underground, we can use single wall sumps because that is the secondary containment for the piping. So there are a lot of variations in there, and I know everybody's from all around the country, so I'm not going to go into too much depth in the particulars, but we will assist you with making sure that your system is appropriately contained for your location. One way, by the way, to tell by looking at a tank if it's fiberglass or composite is, for example, the lower left, that tank has rounded ends. That means it's a double wall fiberglass. If you see an underground tank cylindrical like that has flattened ends, that's a composite. And I think there are a couple of variations to that, but generally that's going to be generally true with most of the manufacturers. So that's a double wall FRP tank there. So component locations, basically where are the ASTs or USTs located on the site versus the locations of the generators or the polishers, the controllers, etc. How far do we need to run the pipe? And of course, are we intersecting any roads or sidewalks? Do we need to go underground, overhead, that sort of thing. And also, of course, this is a high rise with generator on upper floors. Once we get up to a certain height, depending on the types of pumps that we're using, we may need to actually switch the types of pumps that we are using, or we may need to use an intermediate arrangement with mixing different types of pumps. So without going into too much detail there, basically gear pumps are going to be able to push a lot of pressure, a little lower volume. Submersible pumps, like you would use on a typical hospital system with underground storage tanks, they move a lot of volume. They're high flow, but won't push a lot of pressure. They won't push a lot of head feet to get up to upper floors. So that's another thing, of course, we're going to be looking at as far as, you know, where these different components of the system are located. So section 2, you want to take over here, Dave, for a little bit?
Sure. Go ahead and advance the slide. We're gonna kind of go into some detail of where these components should be installed, and the way we're going to do that is by going into some fuel schematics and kind of building up a fuel schematic one step at a time. But we're going to start with working through an example of how you would come up with the amount of fuel you need for a storage system. And in this example, you know, Lee talked earlier about usually the amount of fuel you're required to have on site can be dictated by state or local code, or it could be company policy, or it could be up to the engineer. And in this case, we're going to use 72 hours. 72 hours is our desired runtime.
I apologize. I don't know why it's not advancing. Just give me a second here. Okay.
There we go.
Sorry about
Okay.
that.
So in this example, we've got 4 2-megawatt diesel generators and a runtime of 72 hours. Now there's a handy formula for determining how much oil consumption you're going to have with each generator.
There we go. Sorry about that. I don't know why it's not advancing. There you go.
All right. The rule of thumb is 7 gallons per hour per 100 kilowatts. Or I seem to like the math better. I just take the watts and I multiply it by 0.07, and that gives me the gallons per hour. And the cool thing about this conversion is it doesn't really matter what type of generator or who the manufacturer is. They're all going to be pretty close to 7 gallons per hour per 100 kilowatts.
Well, there we go. Sorry.
All right, so each of our 4 generators is 2,000 kilowatts, and using our 7 gallon per hour per 100 kW, you get 7 gallons per hour times 20 is 140 gallons per hour per generator. So each generator is going to consume approximately 140 gallons per hour.
Dave, I'm going to hand over control of this to you because for some reason it's funky when I try and advance the slide. Okay.
I'm not even sure it's going to let me advance the slide since you're the presenter.
The perils of live slideshows.
I know, we usually record these things, and now I know why. My standard in the past was I always wanted to have better technology than the Joe Biden live webinar. And usually we pull that off, although it didn't seem to hurt him any in the long run, did it?
You know, this is going to end up being you're going to have to launch the presentation and everything. So
yeah, that's why I'm stalling. I've got the presentation going on my screen now. So
this is are you good, David?
I think so.
Okay.
Well, we'll see if my enter button works.
If you need a couple seconds to get stuff, we have some questions. So just let me know if you need a couple seconds.
All right, I'll tell you what, we'll work through this section and then we'll take the questions we have.
Okay,
I
great.
think
So-
we'll leave you in control of the presentation too, from now on.
All right, we'll
even
see how
when I
that
take
works.
over. Okay.
Okay, so in the previous slide, which seems like days ago, we calculated 140 gallons per hour per generator times 4 generators in our example. This is math I can almost do in my head. We're up to 560 gallons per hour of total consumption. All right, my enter button works. So now 560 gallons per hour times 72 hours is 40,320 gallons. And we're almost there. We need 40,000 some odd gallons of usable available fuel. That doesn't mean you can go out and order a 40,000 gallon tank, because there's two things. There's ullage. I think ullage is the right way to say that. You can't fill a main tank up 100%. In most jurisdictions, the fire marshal is going to tell you you don't fill that tank up above 90%. And when they come out and inspect a new tank, they want to make sure that alarms go off and valves start to close when you get to 90%. So you can't use the top 10% in a main storage tank. Also, the drop tube doesn't go all the way down to the bottom of the tank. We typically leave about 10% on the bottom of the tank. And the reason for that is if you get any water in the tank, and these tanks are vented to atmosphere, so they will accumulate water. The water is heavier than the oil, of course, so it's going to go all the way to the bottom of the tank. And the water can contain bacteria that will eat the oil and produce sludge. And the sludge is going to live right in the boundary between the water and the oil. So we want to keep that level below 10% so that it doesn't get to the drop tube. By the way, if we do a filtration system or a fuel polisher, the drop tube for the fuel polisher will go all the way to the bottom of the tank, because that's where the water and that's where the sludge is. But the drop tube for your transfer pumps usually stops about 10% up. So there's only typically only about 80% of the total volume of the tank is usable. Yeah, so for the transfer pumps, the drop tube gap is usually about 6 inches. And for the polisher, it'll go all the way to the bottom and end in a T, or it'll sit about 4 inches above the striker plate. You also get to use the oil stored in the day tanks as usable fuel as well. So if you're not quite up to your 72 hours or whatever is mandated at the plant's location, you can count the fuel in the day tanks towards your 72 hours. And day tanks are usually limited to about 660 gallons, but belly tanks on outdoor generators are virtually unlimited. I've seen belly tanks be 5,000 gallons. So that can be a significant amount of fuel that's stored right in the belly tank. You need to be careful with this. There was a company in Dallas recently. They're a major calculator manufacturer. They had a fuel system for one of their buildings that had a large day tank and a small main tank. And they filled their day tank, and then they had a truck come in and top off their main tank. So everything is full. And then for some reason, a return pump came on, and the return pump overfilled their main tank, and they spilled about 300 or 400 gallons of fuel, which fortunately did not leave the premises. So it wasn't as bad as a spill that left their dirt, but it was still a pretty major spill. So normally day tanks are small enough that you can empty out a day tank, and it's only going to add to that 10% ullage, and it's not going to overfill the tank. And there are safeguards in place in a preferred system to make sure that a day tank return pump can't overfill a main tank, but sometimes safeguards fail. And by the way, with a preferred system, even if you put a pump into hand we don't allow you to overfill either a day tank or a main tank, because operator error is actually probably the leading cause of overfilling a tank. Another thing to consider is that in some jurisdictions, you can't have what they call a wet fill pipe. Especially in high-rise buildings, you sometimes have to use a dry fill pipe. So after you've used that fill pipe to fill a main tank or fill a tank on the roof, you have to drain that fill pipe because they don't want the oil sitting in that fill pipe. So that volume has to be taken into account as well. So summing all this up, in our example, we needed about 40,000 gallons of usable fuel. We've got 10% of ullage at the top of the tank we don't get to use. There's 10% of the fuel at the bottom of the tank that we can't get to because our drop tube doesn't go all the way down. And then you might add 5% or so for generator testing or exercising the fuel system. And in this example, that gets you up to 50,400 gallons. Now, that being said, in an emergency, I don't think anyone has ever said that they had too much fuel. Our representative in Puerto Rico, Mario Franciscini, said he spoke to many facilities after Hurricane Maria, and a lot of them wish they had more fuel storage on site because it took a while for the roads to clear, and then even when they did clear, fuel truck deliveries were intermittent. So when possible, and when you have the space, round up. So if you have large day tanks, you can use the fuel in the day tank towards your desired runtime. And in this example, we're using 1,500 gallon belly tanks. So 1,500 gallons times 4 times 80%, because you can't get to 100% of the fuel in your day tank either, comes up with 4,800 gallons. So to be conservative, I round that down to 4,000 gallons. And then instead of 50,000 gallons to meet your 72 hours, you would only need 46,000 gallons for a main storage tank. Although if it were me, I would probably round up anyway and get back to a 50,000 gallon tank. All right.
So, hey, I
Michael?
just wanted to interject something real quick here. Some jurisdictions like out here, we can go 95%, but I would still use the 25% number to make sure that you're well covered. And I wanted to mention one other thing too, and that is, for example, like OSHPOD hospitals out in California, they need 133% nominal capacity. So I would keep that in mind. If you're working on an OSHPOD hospital, we go even over and above the 25% extra. So I would keep that in mind. And then on top of that, of course, that's a minimum. So if you want to exercise your generators, we definitely want to throw some extra fuel on top of that. So every time we exercise the generators, we don't have to order more fuel. You know, we want to have some extra fuel there.
So that 133% is just a safety factor that OSHPOD requires?
Yeah.
Okay.
And I think it's an excellent idea. I wanted to mention one other thing. One of the comments that we've gotten in our questions in the questions section is looks like Nicholas mentioned that Tier 4 data centers require 96 hours of backup. So that's a really good thing to know. If it's Tier 4, it's going to require 96 minimum. And again, extra fuel on top of that is great because that's, you know, the bare minimum. But I just want to say that was a good comment as well.
Michael, this would be a good time. If we have any other questions in the chat, why don't you hit us with those?
Sure. Let me just start from the beginning. Someone asked if we could talk about the difference between using B20 or B100 biofuel instead of number 2 oil. So we can go over that later. I know we have that later in the presentation, correct, David?
I think so. We don't see a lot of generator projects using biodiesel. Biodiesel doesn't last as long as number 2 oil. It tends to accumulate more water than number 2 diesel, so it requires more frequent polishing. So we just don't see very many generator projects that use biodiesel, either B100 or B20. However, we're seeing a lot of boiler projects that are using biodiesel and a lot of other renewable fuels so the facilities can reduce their carbon footprint. And in addition to B20 and B100, we work with a company called Ensign that makes renewable fuel oil. And we work with a company called REG, who's the largest supplier of biodiesel in the US. They make a fuel called biodiesel residual oil. We actually burn this in the 2 boilers at Preferred's facility. And if there is another facility that wants to convert to this 100% renewable fuel, we can help you out. We have about 3 years experience of burning it in our plant. But we don't see these renewable fuels yet in emergency diesel generators. Although, Lee, if anybody would, it'd be you guys out in California, right?
Yeah, and yeah, I wanted to mention something real quick. There may be a lot of people on this seminar that don't know that Preferred Utilities does a lot more than fuel oil. We have a nuclear division and renewable fuels and all sorts of things. So don't hesitate to ask us a question that you think may be outside of you know, the topic of this particular slide. I do fuel oil only, but don't hesitate if you have questions about renewable fuels or any of this stuff to go ahead and give me a call, because I may not have much information or be an expert in it, but chances are I know somebody who is, who I can refer you to, or other people in the industry, that kind of thing.
I feel like if somebody stumps both you and I, they should get some sort of Preferred swag, like one of those nice Preferred jackets.
Right, or a cup with a logo on it. So I did want to mention one other thing too. I really don't deal very often with renewable fuels out here in California, because most of what I do is emergency generator related. There have been discussions in the past. I have had some experience in the past with ethanol E85 stations and that kind of thing in a previous life. But I did want to mention one thing that is important when discussing biofuels, and that is to get in touch with the generator manufacturer, because generator manufacturers a lot of times may approve a particular blend, say maybe up to B20 or maybe even higher, but it has to be fuel grade biodiesel. It can't be homegrown, and every manufacturer is different. So if you're talking about biofuels or biofuel concentrations, I definitely would talk to the generator manufacturer about their warranty and that sort of thing as well. So I just want to throw that in there.
All right, Lee, you want to take the next section on tank redundancy?
Sure. So redundancy, obviously another important aspect, especially in reference to data centers. As an example, we're kind of back to our blue type examples here in our sort of hypothetical project example. We're going to get to redundancy at this phase, and we're going to say, hey, in our example, we're going to use a 2N redundancy site. So you have basically a fully redundant site. So in our case, we've got 4 generators, but we're changing it up a little bit and saying only 2 of those are actually needed for full load. So at that point, if it's a true 2N site, meaning the owner needs to have a full 2N system from end to end, then in this case, we're going to use 2 separate fuel tanks, 20,000 gallons each, with redundant controls, redundant piping, etc. So basically, at this point, we are looking at having 2 complete systems parallel installed next to each other. So, and I know we had changed it up a little bit with 25, 50,000 gallons, so 25 each. So just ignore that part. But we're you know, at this point now, all of a sudden, okay, maybe a 50,000 gallon tank isn't going to work because we've got a 2-end site. So now we've got 2 25s. So, and I realize in the photo there, those tanks don't match, but we'll get past that. So, Dave,
Okay.
you're advancing the slides.
Do you want to go over some more questions before we start? Keep going, David, or?
Sure, go ahead.
All right, so we did have another question. It says, will an above ground tank with UL 2085 rating installed inside a building require to be installed in a 2-hour rated room? So if a 2085 is installed inside, is it required to be in a 2-hour, I'm guessing, fire rated room?
I would say generally yes, and you'd also probably have a size limitation, which out here usually is 3,000 gallons max.
Awesome.
That's really a question that can vary. The answer depends on where you are and the authority having jurisdiction. That's one of the things they're going to want to weigh in on.
Yeah. Keep in mind, I'm from California, Dave's from Texas, so the answers you're going to get out of me are usually going to be the most conservative. So just take that with a grain of salt.
Here in Texas, you can get away with a lot more. I mean, the oil came out of the ground, right? What's the harm of putting it back in?
Another question we had is, can you talk a little bit more about interstitial monitoring? So I know we talked about that earlier, but Lee, do you have any extra comments on that?
Interstitial monitoring, there's going to be the interstitial on the tank. Interstitial monitoring on an above ground storage tank is generally just going to be a physical leak detector. You may use a float type. You can use I of course can't think of the word for it right now.
Discriminating leak detector is the word.
Discrete. Yeah, you can use a leak detector that will alarm on oil versus water. And I'm just going to go through this really quickly. On underground tanks, same thing. If it's a vacuum monitored tank, you can use a discriminating leak detector. On double wall fiberglass tanks, the interstitial, as I said earlier, will be brine or polyglycol, and that's hydrostatically monitored. So the polyglycol doesn't have a lot of thermal expansion. So as the temperature changes, the polyglycol stays pretty fairly level. So what happens is if it drops below a certain level, it'll drop a float or set off a sensor, or if it's leaking into the ground, or if the tank is somehow compromised and it's below the water table and the water table is actually filling up the interstitial space, then that'll make the level go too high in the hydrostatic leak detector. That'll set off a high alarm. So those are as far as tanks go. As far as piping, we on the vacuum portion, we vacuum monitor the underground portion of the piping secondary piping interstice, right, between the primary and the secondary. Only on the underground portions of the piping with a system that is a pressure system, meaning we're pushing the fuel out of the tank. There's no suction line. So the pumps are submersibles, they're in the fuel, they're pushing the fuel out of the tank. If we have a leak in that case, we want to make sure that is detected. So that will be sent off by one of the floats in the vacuum monitoring system. As far as the above ground piping goes, once it goes through a transition sump and transitions to above ground piping, like steel piping in most cases, that interstitial space only needs to be monitored with low point type leak detectors, like simple floats in a tray or that sort of thing. We don't need to vacuum monitor the above ground portion of the piping.
We can also do cable leak detection. So we've sort of teamed up with Permapipe. We've incorporated the microprocessor board of their PAL-AT cable leak detector system and put it into the control panel of a preferred pump set and made that talk to our color touchscreen. So we can do cable leak detection using a Permapipe system that's basically embedded in the preferred control system. And everything, you view everything and access everything through the same touchscreen, and it's pretty cool.
Yeah, the neat part about that is you can pinpoint the location of the leak itself. So you could use it vertically in a high rise if you were to be so inclined, or a really long horizontal or almost horizontal run underground. The nice thing is, based on how the cabling system works, I guess is an impedance based. It will actually pinpoint the location within a couple of inches or better, I think, depending on how long the line is. So if you do have a 300-foot run, you know, basically, you know, right where the leak is actually occurring, even though you can't see it. So it's a neat advantage.
It tells you where to dig.
Yeah, it tells you where to dig. So, you know, if you lay this out in a data center type environment too, and loop it around, as long as you have a map of the cabling, you could pinpoint a water or an oil leak, like on a grid, and know exactly where, you know, hey, there's a hole in the roof and it dripped through the false floor, that kind of thing. So it's pretty handy stuff. So the next part of our example here is we're going to start looking at the piping layout, and typical suction type system with an underground tank, which is not all that popular, but it does definitely occur. We definitely do these every year. A typical suction piping layout is you have a foot valve in the underground tank, and you're actually physically pulling the fuel through a suction line up into the pump set. So there are things that you want to look out for here. You want to make sure that you can maintain prime. A priming apparatus of some sort, like a priming tee, can be handy here. You want to make sure you have a good foot valve, and obviously a good pump set that you know, usually positive displacement, that will be able to self prime and purge air and that sort of thing. So at that point, you also have on the pump set a relief valve, which you can see in this slide as well. In case there's a blockage, somebody has a valve closed, or there's some sort of issue going on, the relief valve will tie the discharge of the pump set back into the return line to make sure that we don't overpressurize anything. Above ground tank, very similar. It's just you have a little bit you know, easier time as far as suction lift, but basically the same arrangement there. And we're going to look at, of course, all the usual pipe friction loss and that sort of thing, but we're also looking at suction lift. And specifically in the case of having an AST above ground, where you've got the tank higher than the pumps, we have to have an anti-siphon valve. And this is often overlooked or is inappropriately placed. The anti-siphon valves will only work on the suction line. So we have to literally orient the valve in a specific way, and the fuel needs to be pulled through the anti-siphon valve. There's not going to be any sort of anti-siphon valve on the discharge line, which of course makes sense. But they're going to be required on these AST systems. And again, that's going to be part of the calculation. We've got a certain amount of suction resistance with the foot valve, as well as the anti-siphon valve, which essentially has a spring in it. So we want to take those into account when we're doing our suction lift and friction loss calculations, and we assist with that. We actually make software that does that. So
yeah, and some people will put a solenoid valve or a motorized valve there, but the point of the anti-siphon valve is anytime you have fuel stored higher than your fuel system, you run the risk that if you get a leak in that fuel system, that you can siphon oil out of the main tank. And the leak could be something, you know, as stupid as a union that's just not tightened up all the way, or a flange that's not tightened up, and that'll drip out and it'll siphon oil out of the main tank.
Yeah, every fuel tank, above ground or below ground, is fuel is introduced or removed from the tank through a drop tube that goes down to the bottom of the tank. So that creates an obvious risk in some cases of siphoning out the entire tank if that pipe were to break. The only variation on that is if you have a physical day tank overflow. Let's say you've got an underground tank and you don't have return pumps, you're actually in order to prevent overfill, you have an opening at the top of the day tank, and you have a continuous downward slope back to the underground storage tank. In most cases, that's the only time where you're not actually introducing or removing fuel through a drop tube that goes to the bottom of the tank. So that's why we have siphon precautions. So if we have multiple main storage tanks, it's basically the same arrangement, but we have motorized ball valves. Essentially, they're referred to as tank selector valves. So this is a fairly popular solution. Many of you who are watching this have probably dealt with this and seen our designs on this, but basically they're tank selector valves. The nice thing about the motorized ball valves is using particular models that have end switches. So the controller can confirm the position of the valves prior to activating the pumps. And that's handy in case one of the valves is frozen in a particular undesirable way. The pumps will refuse to pump. They'll refuse to activate. So our controller will monitor the positions of the motorized ball valves and then switches prior to actually moving any fuel. If there is a valve that is stuck in an unfavorable position, in most cases you can actually go out there and physically turn the valve so that you're not dead in the water on a particular tank. And they usually have isolation valves on either side so that that valve can be serviced in the meantime while the system is up and running. So they're pretty handy to have, and they help with the control system. So discharge piping, typically, again, from a pump set, will go straight out to the day tank. The flow switch, however, if the flow switch does not make when the pumps activate, then that'll tell the controller there's a problem, there's a potential pipe break, something's wrong. It will, in most cases, try and switch over to the lag pump. So it'll try the lead pump first in a duplex system. It'll say, hey, maybe the pump isn't working. I'll try the lag pump. If the lag pump fails, then it's going to send out another alarm. It'll say, okay, pump one failed. That'll be alarm number one. The flow switch still doesn't make after the lag pump. It'll say, hey, there's a problem. You need to check this. Is there a leak in the pipe? Did somebody break the pipe with a forklift or something like that? So,
or did somebody just close the hand valve so that we can't move fuel?
Yeah. Did somebody shut off the ball valves altogether?
Yeah, I'll take this slide, Lee.
Okay.
So I've been doing this presentation for a while, or a version of it, and I realized I was leaving out a very important part, and I hadn't drawn in the engine fuel pump, which is really a really important part of the system. I've drawn it outside of the generator enclosure because it's easier to draw, but actually that fuel pump is inside the generator enclosure and attached to the engine. Two things about that engine fuel pump: they're limited to about 6 inches of suction pressure, which is not very much. and they can't tolerate very much positive pressure. So these engine fuel pumps are relatively fragile, and that's why you're always going to see, well, I shouldn't say always, because we do headered systems too occasionally, but most of the time you're going to see either a day tank right beside the generator or a belly tank right under it, because with a day tank right there, it makes it easy. The fuel is always going to be between that 6 inches of suction and a couple of pounds of positive pressure that the pump can take. And the engine pump is piped this way 90% of the time, where we draw from the day tank and return to the day tank. The other thing about that engine fuel pump is the flow is usually 3 to 4 times the generator consumption. And you have to look closely in the generator submittal to find the flow of this pump. Sometimes it's not easy to find, but we really don't care what the flow of this pump is when we're returning back to the day tank, because the net fuel that the engine uses is just the engine consumption. So when we're sizing transfer pumps, we really don't care what the engine fuel pump flow is, unless we pipe the system this way. And the difference here is that the engine is returning directly to the underground storage tank in this case. And there's 2 reasons why we might do this. Not only does the engine use that fuel to burn, that fuel is also used to cool the generator. So the fuel going back to the day tank can be relatively hot. And if we have a large generator and a small day tank drawn this way, where we're returning back to the day tank, the oil in that day tank can get pretty warm. And after above about 125 degrees, the engine manufacturers get nervous, and you could have to derate the engine output based on the hot oil. So when we've got a large generator and a small day tank and a hot environment, someplace like Texas, sometimes the system will get piped this way, where instead of returning back to that day tank and overheating the day tank, we return right to the underground storage tank, or right to the main storage tank. And the main storage tank's usually going to be much larger than the day tank, so there's more fuel to absorb that extra heat. Now, if we do pipe the system up this way, now we do worry about the engine fuel flow rate, because now the transfer pumps have to overcome the engine flow rate for each of the generators. So our transfer pumps are going to be 3 to 4 times larger when it's piped this way. Another reason we may pipe it this way is because in Los Angeles, we're limited to 60-gallon day tanks. So virtually any size generator returning to a 60-gallon day tank in a warm climate like Los Angeles is going to overheat that day tank. So you'll see a lot of systems in the LA area that are piped like this, where the day tank is really just kind of a supply day tank and not a return day tank. There's another thing we can do for overheating. We can go back to this, where we pipe it the traditional way, but we'll put a thermocouple down in the day tank to monitor the temperature of the oil in the day tank. And if that oil gets above set point, then we'll activate a return pump and pump out some of that warm oil, and then trigger the transfer pumps to come on and replace that warm oil with cooler oil out of the main storage tank. And that's referred to as level bouncing in places where it's pretty common. So we're right at 3 after the hour, and we thought we would do a break every hour so that people can hit the restroom or return a phone call. Instead of a dead screen, Michael, I think let's change things up and let's do 5 minutes of answering questions in the chat before we go back to the presentation.
Sure.
To give people a chance to take a bio break.
Sure. Yeah, no problem.
Okay, so we will come back at about 10 after the hour.
Okay. So do you want to go ahead and switch the control over to me?
Not sure I know how. Oh, change presenter. Okay, Michael, you should be the presenter now.
Okay, I got it. Thank you.
You got to hit play on your little timer there.
Who says we don't understand technology? All right, Michael, do we have any questions in the chat?
Yes, I've got some questions here. Talked about interstitial monitoring. Here's a question. Suggestions on walling the pipe going up to the high rises. So double walling pipe in situations.
Don't
Lee, you
everybody
want to
talk
take
at
that?
once?
That's more your area of expertise than mine.
I mean, typically double wall pipe in a high rise will be schedule 40 primary with schedule 10 secondary with a low point leak monitor, maybe a float. It could be a sealed secondary with a simple float type in the bottom. Another way to do it is to use an approved type of piping like Omega Flex, something that is pre that is already double wall and is flexible and maybe a little lighter weight. That's always an option. A way of monitoring that, as Dave mentioned before, also would be to use like a PermAlert cable leak detection system. Not as popular, but definitely an option and kind of a nifty one. But generally, as far as interstitial monitoring goes, in a high rise, that's above ground pipe. So in most cases, like I said, it's going to be double wall steel and have a low point leak detector. If it's a very tall high rise or something like that, you have a lot of different runs. You could zone it if you wanted to. That way you would know approximately where, if a leak occurred, you'd know approximately where it was. And in most cases, I would say though, once the piping, primary and secondary, is pressure tested and everything, generally it's just going to be a low point leak detector.
But Lee, in general, you're going to need double wall piping anytime the fuel piping goes through the occupied portions of a building, correct?
Yeah, and in certain locations, San Francisco being an example, not only is double walled, but it's softed with fire resistant soffit. So again, it really depends on the jurisdiction, but yeah, in almost every case, I think it's really going to be at least double walled. Some places will allow spray type, fire resistant insulation. Some will require soffits, as I said. But yeah, that's going to be jurisdiction.
In New York City, it's very common to have the secondary containment piping run into a 55-gallon drum in the basement, and then you put a float switch in that 55-gallon drum to tell you when there's oil in it.
Yeah, we can't do that out here, but we are working on an interesting solution for that as well, where we would be able to actually drain a riser pipe.
The primary.
Actually drain the primary. In the larger high rises where the secondary is sealed, a lot of times there will be a ball valve in the bottom. So in case there is a leak, we don't just run it out into a spill pan and overflow. A spill pan will actually be able to contain it in the pipe until such time that we can provide some sort of vessel to recover that leaked amount of diesel and hazmat it away somewhere. So, there are some precautions that can be done to make sure that that even if there's a leaking primary, we're still not spilling any fuel. We've still got it contained. And there are several different ways to do that.
Okay, awesome.
Yeah.
Let's go back to the presentation to keep things moving. If you want to give me back control, Michael. And
sure,
if anybody did take a bio break, you missed a good question about double wall piping inside of buildings. And if you're dying to know the answer, you'll be able to see this webinar on our YouTube page in a couple of days. So, so we were talking about the two different ways to do the return piping, and we showed the engine fuel pump and how it's pretty picky about the pressure going to it. No more than about 6 inches of suction and a couple of pounds of positive PSI. And this is the traditional way of piping it. And then the alternate way of piping it is, sorry. This is the alternate way of piping it, where we return directly to the underground main tank. And the only concern there is that now the transfer pumps have to keep up with all of your connected engine fuel pumps. So adding on to the fuel schematic, if we have more than one day tank, we simply put all the day tanks on a supply header. So we're going to pipe them basically in parallel. And then to make sure we only get fuel to the day tank that's calling for fuel, each of the fill manifolds on the day tank will include at minimum a normally closed solenoid valve. And the sequence is, when the day tank calls for fuel, we'll bring on a supply pump, we'll prove flow in the supply pump, we energize a solenoid valve for that day tank, and then we top off just that tank. And that fill manifold, sometimes it really is just a solenoid valve. Often there's a 3-valve manifold around that so that you could bypass the solenoid valve. Sometimes there's 2 solenoid valves. Sometimes the 2 solenoid valves are turned into 1 motorized valve. You might have a Y strainer there. You might have a sight flow indicator to let you see that oil is going into the tank. And you might even have a flow switch there so that we make sure if day tank 1 is calling for fuel that we actually detect flow going to day tank 1, which is an important thing. And we can do any of those combinations, but most common is probably just a solenoid valve with a 3-valve manifold around it. So Lee talked about tank selector valves in the supply line. You also are going to need tank selector valves in the return line as well. And we highly recommend that if you're drawing from tank 1, that you're only allowed to return to tank 1. This makes the system somewhat intrinsically safe. And then what we'll do is, if the operator says, through our color touchscreen, if we're going to run on tank 1 today, we're going to line up the supply tank select valve and the return tank select valves for tank 1.
Sorry, I'm in the middle of a webinar.
And again, we like to use motorized valves because the motorized ball valves are less likely to leak, and we can prove the position. There's a very large data center in San Antonio that had headered return lines and solenoid valves that leaked a little bit when there was pressure on the system, and eventually it leaked enough to fill a tank to 100% and overfill a tank. And fortunately, it was a 24-hour staffed facility, and the person on staff heard oil hitting the ground immediately and figured out what it was and shut off the oil to that tank. So that's the reason why we usually like motorized ball valves in this situation. We like to pull from and return to the same tank. It makes it intrinsically safe so that you can't overfill that tank. Some facilities want to use the transfer pumps to move fuel between main tanks, and we can do that, and we can interlock it to make sure that it's safe. But we would prefer to do it more of an intrinsically safe system and not rely on a float switch to make sure we're not overfilling a tank.
I just
And
wanted to mention, just add something onto here real quick, too, that the system itself, and this we can discuss with the engineer, the control procedure here, but every time the system goes on, you can have the controller say, hey, their generator's asking for fuel. Which tank should I use? I believe that the general default way is whichever tank has the most fuel in it is the one that is selected. There can be other situations too. We can have it set up controls wise that it'll alternate between the two tanks every single time there's a new call for fuel. Obviously, also when one of the tanks, if it were to get to a low enough level, the system will automatically switch to the other tank. It's not something that has to be done manually. So there are all sorts of different control strategies there that we can discuss with engineers when we're working on a system like this.
Okay, I don't think there's actually any new information here on this slide. But our previous graphic artists figured out how to do these animations, and they're really cool. You've got to be really careful about valves in the return line. The strict interpretation of NFPA code is you're not allowed to have any valves in the return line. But when you have multiple tanks, you need some way of directing fuel back to the correct tank. And when you have return pumps, you need a check valve there to make sure that you don't flow oil backwards and use the oil in day tank 1 to fill day tank 2. So we've got to be real careful about valves in the return line, and that's another reason why I like to use the motorized valves, because the actuators have proof of open and proof of closure switches on them so that we can make sure that our valves are lined up when we go to energize return pumps. So this animation shows a typical control sequence. So the generator's using fuel. We typically put 4 float switches in a day tank. It's called a PLS4. And the pump on float switch is at 50% level. And when you hit that 50% level, then we open the fill valve to that day tank, we energize the supply pump, we prove flow, and we fill it up to 80%. At 80%, we hit the pump off float switch. And then your day tank is topped off and the fuel system just kind of goes into hibernation mode. If you blow past the 50% pump on switch and get down to the 40% switch, that's the emergency low. Now alarms start going off in our control panel and we energize both supply pumps because for some reason we didn't top off like we were supposed to. And then on the other side, if for some reason we get past 80% full and go to 90% full, then the top switch in the PLS4 breaks. That sounds an alarm because it's an upset condition, and we will cut power to the fill valve that's shown there in the schematic, and we'll activate a return pump. And when we cut power, it's actually a hardwired thing that can't be overridden by the operators. So if you've got a day tank that's 90% full, you won't get power to that solenoid valve. And if there's only one day tank in the system, then we're going to cut power to the supply pumps as well by de-energizing their motor starters. So it's not an easy thing to even jumper. And we do that because one of the most common ways of overfilling a tank is operator error. Now, the 40, 50, 80, 90% levels are completely arbitrary, but they're completely right. I've worked on other day tank systems where the pump off switch is at 100%. And it was very scary filling that day tank because, I kept checking the level. I'm used to them shutting off at 80 or at worst 90, and this tank went right up to the top. You don't want to get that high because if you plan on shutting off your fill valve or shutting off your supply pumps at 100%, if you get an upset, you're pushing fuel up the vent right away, which is a very bad thing. At a normal shutoff of 80% or an emergency shutoff at 90%, if something's going wrong, at least you've got 10% of the oil volume there to give you time to figure out what's going on with the system. And by the way, with a preferred system at 90%, alarms are going off all over the place. So it should get the attention of one of the plant people to figure out, why is my day tank overfilling? And that 10% gives you a little bit of time to figure out what's going on.
Yeah, I just wanted to add something. If you can go back to that drawing. Two things real quick. Dave was mentioning when it gets down to that 40% critical load, both pumps go on. So in a situation where we're commissioning that sort of thing, you might have 4 day tanks and they're all empty. What you'll notice is that they're going to fill up a lot faster than normal because we're in that low situation. So both of those pumps are going to fire and they're going to fill up those tanks a little bit more quickly. It's kind of a minor thing, but I want to throw it out there. The other thing that I wanted to say that's more important is Dave was talking about level bouncing before for thermal issues. The level that when the day tank goes through a level bouncing sequence to bring the temperature down, you would see a resistance temperature detector probe that's not shown in this drawing, but it's a good drawing to illustrate level bouncing. The levels that you're bouncing between are the 50 and 80%. So the return pump the RTD sensor will say, hey, there's a high temperature situation here. I'm going to turn the return pump on. It'll pump down to that 50% level until that switch drops. And that'll signal the supply pump to turn on and the inlet valve to open, and it'll pump back up to 80%. When it gets that back up at 80%, the supply pump will shut off, the valve will close. The RTD's going to continuously take temperature readings. It's at that point going to say, hey, what's the temperature like? It's still too high. So it's going to boom, immediately start another bouncing sequence to exchange the fuel with the main tank. So I just wanted to point out, this is a good diagram for that. It is between the 50 and 80% levels as you see on that particular day tank. That's where we're bouncing the fuel. We're not draining the tank all the way down and filling it back up.
Yeah, and the pump on level at 50% is pretty conservative. It gives you quite a bit of time. You've got a lot of generator runtime even at that 50% level. And,
yeah, hopefully an hour or two.
And this is probably a good time to mention, our spiel for return pumps. If you're commissioning a system and let's say it has gravity overflow and you've got an underground tank and you can gravity overflow all day long, if you're the tech out there commissioning the system and you get up to that 80% pump off level, you're done because there's no way besides running the generator to take fuel out of that day tank. And it seems like whenever I'm out on a fuel system startup, it's usually a new generator and they don't want to run it without the technician being there. And besides that, the generator is a really slow way to get fuel out of the day tank. Energizing the return pump is going to suck down that day tank really quickly, and it allows you to test another cycle with the supply pumps. And not only for technicians, but also for the facility. It's not a terrible idea to once a week or once a month, or if there's a storm out there in the Gulf of Mexico threatening you, go activate your return pump and pull the level down to 50% and make sure that the supply pumps kick on like they're supposed to and top off your tank. And then your system's ready to work and you've exercised it.
And it's also really handy just to pump the tank down to exchange the fuel of the main tank so that your filtration system can, turn over the fuel in the day tank every so often to make sure that the fuel in the day tank gets polished as well, because that's the fuel that's going straight into the generator. So we want to turn that over, sometimes exchange it with the main tank.
I think that's it for the flow diagrams. And now we've covered most of the generator scenarios that we see. Lee is a 100% fuel oil person. I also do boilers. And for boilers, we would go back to a headered system like this And we'd probably put a back pressure regulating valve on the end of that supply header to maintain the pressure that we need through that whole supply loop. And boiler projects are usually simpler than generator projects, but the one difficult thing about boilers is some boilers have onboard pumps like generators do, and need oil between, you know, slightly negative to slightly positive, and the onboard pump on the boiler will just draw off of that header. Some boilers have no onboard pumps at all, and then that supply header may need to be charged as high as 100 psi for a fire tube boiler, or even 150 psi for water tube boilers. So if you're not sure what the flow and the pressure requirements of your boiler project are, just let us know what the make and model number of the burner is, and if we can't figure it out by Googling, we know people at all the burner manufacturers, and we'll call them and find out what the requirements are of their burner or their pumps. Okay. Lee, go ahead and take it from here. I think these are the slides that you put together.
Okay, so we're at this point really going to start looking at the major system components now that we understand the layout, the piping, and that sort of thing. So this can really, depending on what we select here, can affect the need, as it says, for different types of subsystems, code compliance requirements, et cetera. Once we start selecting some of these components, that can affect the subsystems like priming, suction lift, fuel velocity, et cetera. So we're really, it's just kind of we haven't figured out the whole system yet. Once we put the components in there, that can make changes. And for example, like Dave was talking about returning the fuel back to the main tank versus back to the day tank, that's going to change things. It's going to change the size of the pumps, et cetera. So once we go into this, we may make some changes. So Dave, you're still advancing the slides. First thing is we'll look at gear pumps. As I mentioned before, I'm not going to go into too much detail here. Gear pumps tend to be higher head, lower volume in general. I mean, you can certainly have high volume gear pumps, but these are really good for pushing fuel up higher, higher pressures. Like Dave was saying, on a boiler system that requires higher pressure, we need to use something like gear pumps. But also for remote fills or for shooting fuel up to a rooftop, you know, it could be 100, 300 feet. So, you know, that's a good application for gear pumps. They do require suction line. So there's, you know, we've got a few different components there. We've got a foot valve, a suction line. We may need a anti-siphon valve on that suction line because the fuel tank may be higher than the components. So since we've got that suction line, we have to achieve and maintain the prime. So it's a really good idea in most cases to install a priming tee. Priming tee, for the most part, just consists of a high point in the piping that we put in a T that points upwards with a nipple, a ball valve, another nipple, maybe a cap, so that we can unscrew the cap, open the ball valve, maybe spin on a funnel and literally pour some diesel fuel into that suction pipe in order to prime it, or quote unquote burp the pipe, get the air out of it. Once we have that pipe full, we can close the ball valve, which will close off the fill line, and go ahead and spin the funnel off and spin the cap back on. And now we have a nice primed suction line. We can fire the pumps, and there's going to be a minimal amount of air that the pumps have to deal with and push through the system. This is especially nice feature to have because it takes some of the worry out of making sure that if it did for some reason lose prime, or you needed to service something, that you can easily reprime it. So it's a good thing to have as peace of mind. Again, of course, be mindful of the suction lift. Generally with gear pumps, we're going to use double poppet foot valves instead of single because they have of the priming maintenance situation. And you know, we want to make sure and take a good look at that. The other nice thing about these PLC systems is we can program the PLC, the controller, to say, hey, every so often check prime on the piping by firing the pumps. So there may not be a call for fuel or anything like that, but we can pre-program a priming check to occur however often we need to, every day, every 3 days, and just to fire the pumps and go ahead and basically do a self-check and make sure that the system is still primed.
One thing I'll add to this is, because of suction lift concerns, these positive displacement pumps or gear pumps should be located as close to the main tanks as possible. And even if your main tank is outside, out in the elements and a long ways from your building, we can still put the pump set out there. In fact, we can put a cool telecommunication looking NEMA 3R enclosure over the entire pump set, and it just looks like the enclosures you see at intersections that run the traffic light controls. And they're waterproof and will protect the pumps. And it puts the pumps in the ideal location where all of your piping is discharge piping and you've minimized your suction piping.
Yeah, I should probably change that slide, you know, it's my fault, but I said on small or shallow UST projects, we can do suction systems on larger underground tanks. It's possible. We're going to do some very careful calculations. We're going to mix and match pumps and motors and that sort of thing. So I should probably soften that last part of the last slide. We can do it on some of the larger systems. It's just a matter of we're going to be very careful and go through some pretty serious calculations.
And you can use our online pump and pipe sizing program to estimate the suction at the pumps, whether you have an AST or a UST system.
And we're happy to also go over that with you and do any more calculations or anything, you know, if that makes you more comfortable as well. We can certainly assist with that directly. So obviously the other big pump selection possibility here are submersible pumps. The nice thing about submersible pumps, there's no priming issue. The impeller is actually submerged in the fuel. So it's always pressurized. The fuel always is pressurized anywhere outside the tank, or at least the supply line. The nice thing about them is that they are high volume. They'll move a lot of fuel really fast. They're used at gas stations all over the place. They're very robust. The limitation with these, they're good equipment, but they won't push up a whole lot of pressure. So we don't want to use them on charged boiler line systems, you know, back pressure systems, or really don't want to go up. It says 3 floors there. I mean, we can go up certainly higher than that, depending on which type of submersible pump. We can go up 5, 7 floors, even higher. But generally, we start shying away from using submersible pumps when we've got a high-rise situation like a belly tank and a roof. But it really depends on the application. Again, the nice thing is no suction line, no priming. We can use them on basically any UST project, and they usually are used on USTs. But that does create a pressure situation. So ELD, or continuous vacuum monitoring, such in the state of California, is required on a pressure system. So we're going to keep that in mind. And they're also quite useful on above ground storage tank projects. So again, it's just what's going to be the most appropriate. You know, based on effective and efficient piping, pumping, but also could be a situation that's just a matter of real estate or something like that, or protection of the component. So we're going to take all those things into mind and make the right decision on what type of pump to use. Day tanks, we talked about those before. The 3 types that you see there. On the upper left, that's an open rupture basin day tank. So it's a single wall tank inside of an open rupture basin. Those are really nice for indoor use. They're easy to inspect. And a lot of times will require one less vent. So that's nice. Those side penetrations, one of those may be an overflow, but generally those are going to be attached to drop tubes. So those are not splashing fuel generally. The tanks to the right looks like a big project that Preferred was working on. Those are double wall with controllers. Looks like they're all lined up for shipping. Those are enclosed, and we can use those outdoors. Sometimes we'll use them indoors as well, but that's just an enclosed double wall, pretty much the same, but it's going to require the 3 vents. And the tank in the bottom, basically the same thing. It's an enclosed double wall, but that's a belly tank, base tank for under a generator. The big difference between those really is just the level switches that we tend to use. They're going to have to be shorter, so we may need to, if we have, say, 4 switches on one sensor in the tall tanks above, we may need 2 separate switches with 2 switches each for the bottom one. So we may need more bungs in that tank, that sort of thing. So I'm not going to go through all of the text here. Basically, just keep in mind, the larger the tank, the cooler the fuel generally, as we discussed. As far as sizing goes, 2 to 4 hours of runtime is ideal, but always bigger is better. We want to keep in mind, though, that we do have some limitations as far as how big we can make these tanks, or how big code allows us for them to be. So NFPA 30, we're going to talk a little bit more about that, but basically we want to keep in mind the size of the individual tanks and the total size of all the tanks together as an aggregate, and getting into also where the tanks are, if they're in separate fire rated rooms or whether they're all together. So that's going to affect our day tank size as well. Again, return pumps are always a good idea to prevent overflow, circulate the fuel for polishing, pump the tank down for whatever reason. And also keep in mind, a lot of the day tanks are built to order anyway. If there's a particular application, you've got an egress problem in a confined room, a small room, we can make some different types of tanks too. We may make a tall, skinny one to fit up against the wall and improve a clearance situation that exists in the room that maybe we don't know about in our design. So we may talk to you about the configuration of the room, etc. So an important thing here is at the bottom, the blue part, that is make sure that we specify the sizes of bungs and the number of bungs. We don't want to get into a situation where we don't have enough bungs for the amount of sensors that we're using, or the bungs are too small. We've got too big of a foot valve to go in too small of a bung, that sort of thing. So it seems like kind of a minor part of the system, but the day tanks are extremely important, making sure that they're sized right, that they have the right dimensions, they take up the right amount of real estate, they have enough bungs, etc. So very important part of the process.
And one thing that happens too is if the system is designed around day tanks, Preferred is going to design the float switches and other instruments in the day tank and program the pump controls to work with those IO points. When we're doing a generator system with belly tanks, we often don't know what's in the belly tank. Literally nobody can find the information on the belly tank to see how many float switches are there, how many of the float switches are used by the generator controls are actually available for us, how the leak detection is done, and you end up having to do program changes in the field to try and catch up with the hardware that was provided with the belly tank. So they're super convenient from a real estate point of view because they don't increase your footprint anymore, but they can be difficult to integrate with the rest of your pump controls.
Yeah, that's an excellent point. We do run into that a lot. And I would say, my preference is try and get that's why we like to see the generator submittal so early in the process. try and get as many bungs as possible so that we have spares. And it's definitely our preference to install our own level sensors, just because it's easy for us to, we have less field programming, that sort of thing. But also, if there's an issue at some point, and we pump fuel based on the information that came from somebody else's level sensor, then the finger pointing starts and all this, and it's really good to have just an integrated system with the sensors from the same people who made the controller. So it's just keeps it a lot cleaner and simpler that way. Direct draw systems are really interesting, and basically what they really are is in a conventional system like we've discussed so far, the generator is pulling fuel out of the day tank, basically just doing it by itself. It's just got pretty much an unobstructed line that the generator engine fuel pump itself pulls from the day tank, circulates the fuel, and then shoots it back to the day tank. A direct draw system is a situation where you maybe have a single generator or maybe even 2 or 3, but the main bulk storage tank is sitting right next to the generators, just physically very close to the generators. And there's not really any point of having a bulk storage tank and say 3 day tanks for 3 generators, all piled on top of each other with a bunch of pumps, transfer pumps and everything. As much as we'd probably love to build that equipment and sell it to somebody, if it's not the right thing to do, if it's not the most reliable system, we're not going to do it. The easiest way to do that is to have a direct draw system where the bulk storage tank is literally feeding the generators directly. There are some caveats with this. In the red there, the positive things is it eliminates complexity, so it eliminates the supply pumps, the return pumps, some of the controls, and obviously is pretty reliable. The gotchas on it that we want to look out for: install a priming tee. The generator is not going to want to sit there and try and fire with an empty fuel line. So definitely prime the lines ahead of time. Make sure that you have a priming tee available to do that easily. Definitely be aware of suction lift, especially if it's a small generator and a large tank. If you've got a big generator and a little tank that's low to the ground, a lot easier. But if we have a small generator with not as powerful of a fuel pump, we've got a big tank with a lot of suction lift, we want to make sure and be aware of that, keep the pipes low, etc. Also, be aware of the suction line components. What we don't want to do is restrict the availability of the fuel that the generator is trying to pull. So what we do in most of these cases is, you see in the diagram there's actually an anti-siphon valve shown. I would, and it's certainly possible to do that. We have a new line of anti-siphon valves that are low suction, low head, and that's fine. That's great. Again, it depends on the generator and the fuel tank sizes. What we do in a lot of cases of direct draw systems is we want to have as open and free flowing of a line as possible for the generator, make the generator happy. So we'll use a normally closed solenoid valve that is interlocked with the generator run signal. So when the generator turns on, when the generator says, hey, I'm going to fire up and start, that'll snap that solenoid valve open and give you a nice free flow to the generator. As soon as the generator shuts off, that valve will be de-energized and snap shut, and that'll prevent any siphon. So also, we probably don't want to use double poppet foot valves in most cases. We just use a single poppet or maybe no foot valve at all, depending on the situation. So again, the direct draw systems are sometimes, you may hear me say, oh, well, let's see if we can go direct draw. It'll simplify things. It just depends on the situation, but it is something that we do, fairly often. So it's a good option.
There's another consideration in direct draw systems. The main tank has to be very close to the generator because the fuel pump on the generator is really limited in suction, and the main tank has to be accessible by a fuel truck. So there's got to be a way for a fuel truck to get right to the main tank. And in some facilities that can be designed so that it happens. In other facilities, it makes it impossible. So the main tank has to be, somewhat remote from the generators just because of accessibility to fuel trucks.
Yeah, and we can use remote fills, which is the next part of the section as well. So we may be able to remotely fill that tank. So remote fill ports, there are 3 basic types. On the left is not as common, but that would be an in-ground fill with just the fill pipe by itself under a little cover. But with any type of fill port, or even on a tank that doesn't have a remote fill, we have to have an overfill alarm panel. And so that's the thing right next to it with the bell on it that says preferred. That's an overfill alarm panel. That's for a single tank. That's going to be required on all of these systems. So if you have a very simple fill pipe only in the ground, you're going to see the configuration on the left. Again, not as popular. But you do need to have some wall space, and you have to, make nice with the architect to make sure that there's some place to put that overfill alarm panel where the truck fill operator can see and hear it. And there are even specific distance requirements of that. I believe in California, I hate to say any numbers, but I believe in California, some of it's 25 feet if it's unleaded, but it has to be reasonable. So keep that in mind. Even if you have a nice, in-ground thing, you're going to need that overfill alarm panel. On the upper right, that's what's called a sidewalk spill container, and that's completely self-contained. Does provide the secondary containment, a little pump there in case you need to pump it out for some reason, you spilled some fuel. And it has the overfill alarm panel, as you see in that center photo on the upper right. That is the overfill alarm panel that's built into that unit. So it's completely self-contained, just looks like a manhole on the ground. And the controls point up, so you don't have to crawl in there and see anything, and everything is viewable from the top. The third type on the lower right is, at least in the West Coast out here, the most popular. That is the horizontal spill container, meaning it is wall mounted, either flush or surface. Can also be stanchion mounted, say next to a tank and a tank pad. If you don't want to have a ladder to go up, it's a nice little fill box. We do these a lot for high rises. This particular one has a solenoid valve actually in the fill box, which is not as popular, but it's certainly possible. That one also has a vacuum breaker. So this one was going to this particular one in the photo was going to a tank that was in a below level in a basement, and we wanted to be able to drain that fill line. So directly into the tank. So all sorts of different configurations here. This one has a gallons display, alarm horn, etc. But those are definitely the most popular. We also make a pump boosted remote fill. So if we're shooting fuel up to a rooftop somewhere, we can have a totally self-contained unit with the pump and everything in a cabinet, or we can have the pump set, say, the fill port on the wall on the street, but have a pump set in the basement, one level below, and then pushing the fuel all the way up to the roof, 350 feet. So those are all custom pretty much. It depends on the application. We're going to size the pumps and everything, the pipe sizing and everything for each one of those individually. So it's hard to talk about all of them, but basically those are your different types of remote fill ports.
When you're designing fill ports, you have to bear in mind there's 2 types of fuel trucks. There's a gravity fuel truck like what you see at the gas station in the morning, and it relies on gravity to fill a tank below it. And gravity trucks can be gigantic. There's another type of truck that's called a Bowser or a pumper truck. These are smaller trucks, but they have pumps on them so that they can pump to an above ground storage tank, but they can't pump to a high rise. So even if even if you call out a Bowser truck, its little pumps are not going to be able to pump up to a main tank or a day tank on the roof. So Lee does a lot of these boosted fill ports in Los Angeles and San Francisco, and I see them I do them here in Texas too, because if you've got a pump in your fill cabinet, then you can call either type of truck to get a fill up. You don't have to get, if you have an above ground tank, you don't have to wait for a pump truck. If all they have is a gravity truck, you can use that if you've got a pump in your fill box.
Yeah, and so thanks. That's a lot of good information. So there's going to be the booster pump shooting up to the roof, or if we're filling above ground storage tanks, a single or multiple, generally we refer to those as offloading stations, but it's exactly like Dave said, but we may refer to them as either pump boosted fills or offloading stations. We've looked
Lee,
on
how much
large,
fuel do those little pumper trucks carry?
I think generally they're up to, I mean, it depends on the size. We've seen 500-gallon ones that are like on like a Ford, like a pickup. And but I think generally they go up to about 4,000 or 5,000 gallons.
Okay, so if you've got a big AST, then it's going to take a lot of those trucks, or a pumped fill box, and you can get a gigantic gravity truck to come out and fill your tank all at once.
Yeah, on something like a hospital or a data center, we may have a few semi trucks lined up that are gravity trucks, but that's why we have the offloading station that may have a very large gear pump or even 2 gear pumps with a larger fill pipe, like a 3 or 4 inch fill pipe, like you have out there in Texas at that big data center, the big government data center. It's got 10, 40,000 gallon tanks, big offloading stations on that site, right?
We're not supposed to talk about that data center, and there's a good chance they're listening in on this conversation anyway.
We're not saying any names, but yeah, on the larger systems, I'm working on a couple data centers right now where we really need to put. There's so many large above ground storage tanks, and it's going to take so many trucks that we have to have these large offloading pumps and larger delivery pipes for them, just because you don't want a fill operation to take 4 days, so, but those are generally referred to as offloading pumps or offloading stations as well. So we didn't really get into that here. Maybe we should modify this presentation and include those, but yeah, they do exist. So on piping above ground versus underground, again, some advantages and disadvantages of each. Above ground piping, obviously it's a lot easier and less expensive to install and inspect and maintain. Standard fittings, a lot of very skilled workers who are good at doing a lot of good above ground piping. Obviously less regulations, code compliance. And you can also install above ground piping within concrete trenches, which is very nice, gets it out of the way. Maybe have trench plate over it, or you may even have a sealed trench. The downside is it's more exposed, it's less secure. You might obstruct walkways, that sort of thing. You may have to ramp over it. And it's, it requires a little bit more labor as far as, you're generally installing it in shorter straight lengths, fittings and all that. Underground piping, on the other hand, you can go a really long distance with a single pipe. Some of the underground piping comes in like 300-foot rolls, so you can have a 300-foot stretch without having any fittings or anything like that in it. Obviously, that comes with some caveats. It depends on the situation. It's going to have a bending radius as well, so I don't want to do a hard 90 underground unless it's within a sump. So it's a lot easier to go longer distances and maybe trench more directly to where you need to go because it's buried and you can pave over it or whatever you're going to do. It does require more equipment and specific trained individuals for that. Obviously, more regulations and things to deal with as far as code compliance goes when it's buried, and obviously a lot more site disruption and that sort of thing. Nice thing is nobody sees it. It's not as affected by heat and UV and that sort of thing. And again, a lot less fittings over longer distances. It's important to keep in mind, though, of course, we need to slope underground pipe just like we do above ground pipe. So if we've got, something like 1,000-foot run, it's probably going to be underground, but we're going to have to seesaw the pipe, meaning slope it up and then slope it down, slope it up, slope it down, with sumps in between, to make sure that we can make that length without having a hole that's 12 feet deep, with it's a confined space, in order to maintain that slope. So we can slope up, down, up, down, up, down throughout a run for longer distances. Hopefully that was clear. Materials, above ground piping, again, we went over this a little bit. Generally, and these are generalities, generally it's going to be Schedule 40 steel for above ground, most often. Sometimes on some government jobs, that sort of thing, it's Schedule 80. Sometimes there's a ballistic requirement where they may go to Schedule 80. There are, of course, other materials, stainless steel, as well as poly-coated stainless steel, UV resistant, etc. Something like a Omega Flex, something like that, or a Brute. But generally, it's going to be Schedule 40. Secondary, again, is generally going to be Schedule 10, but could be 40 or 80 depending on the requirements. It may be multi-layer fiberglass, polyethylene. It could be a coated pipe, preloaded, double contained with a poly shield on the outside, etc. We're really going to be looking at these depending on each application. Some of the poly pipes are only for use underground. Some of them are UV resistant, so we can actually install them in areas that may have direct sunlight, that sort of thing. So we're going to look at each one of those. Underground piping, again, generally, it's most commonly going to be high density poly pipe, nylon or fiberglass. Secondary, you see a lot of fiberglass secondary. We see a lot of poly secondary, also stainless steel. I think in most cases, the stainless steel secondary is usually going to have a poly jacket around it. That's most common. Ducting also, I haven't dealt a whole lot with this, but ducting is not really considered a containment layer, but it might be more something along the lines of a rock guard, or if it's a underground situation, it may be almost like a tunnel, so that that piping could be more easily replaced in the future. Maybe it's temporary, you want to remove the piping without excavating it, etc. So we're going to take that into account too. If it's a temporary system, it's only going to be in place for a couple of years, we might look at a solution like that.
Okay, it is pretty close to the top of the hour, so why don't we do a 5-minute bio break again? I'm going to change the presenter over to Michael, and he's going to run the little clock.
Sounds good.
And we'll take a couple of questions off of the chat while we're doing our 5-minute bio break, and you won't miss any of the regular presentation if you're back within 5 minutes.
All right, starting the questions. We have a lot of questions, so if we don't get to your question, I will try to forward it to the correct person to get to it.
Right. And by the way, the most common question we get is, can I get a copy of the presentation? The answer is yes. Just email Michael or Lee or I, and we'll shoot you a copy of the presentation.
And I'm willing to go as long as it takes after the presentation ends to get to all those questions, if that's what we need to do as well.
Appreciate it, Lee.
Willing to sit and listen.
We might have one person that's waiting for the question to get answered, but we'll answer it. A question we had is when we did those calculations for the sizing of tanks, and I know we kind of already talked about this, but is that in consideration for any type of biofuels? So can you use that calculation for biofuels?
You can. The only thing to be aware of in biofuels is sometimes the BTU value of the biofuel is different than number 2. So check your fuel analysis. A tank that's 72 hours on diesel may not be 72 hours because the BTU content of the biodiesel could be a little bit less. So just
Your mileage may vary.
So just check it.
Got it. Someone asked about what is the makeup of the renewable fuel preferred is burning. So David, can you just?
So we're burning a fuel from REG called bioresidual oil. It needs to be heated to about 140 degrees, and we were burning number 6 before, so we already had our pump and heater set there. It comes from 3 major sources. Corn oil that's left over from the production of ethanol. It also includes impurities that are taken out of biodiesel, and it also will include some recycled cooking oil. REG has a network of companies that go out and recycle cooking oil from places like McDonald's, French fry oil, and all the oil goes through a very careful cleaning process. So the oil is super clean, and we've been burning it for 3 years. And every spring we take down our boilers and do a thorough internal inspection, and we're not seeing any unusual sooting or anything inside our boilers. So it's very clean, and because the bioresidual oil is a waste product of really other biofuels, it has virtually no carbon assigned to the bioresidual oil. All the carbon is assigned to the ethanol or the biodiesel. And because this is a waste product of those manufacturing processes, it doesn't get attributed virtually any of the carbon associated with the other fuels. So it's almost 100%, carbon free.
Okay, great. Next question is, any good resources to determine EPA requirements in your region for underground storage tanks? Lee might be the one.
What requirement? I missed that one word.
EPA requirements.
Okay, EPA requirements
for underground storage tanks.
Oh, any centralized source for that?
Yeah, like resources that you know of that for people to find.
I mean, they're going to be sort of no. I mean, the short answer to that question is I'm not aware of any. I mean, we're going to start with NFPA, and then if it's California, maybe we'll look at CDC.
Yeah,
or
you're going to have NFPA
resources.
30, NFPA 37, and NFPA 110 that are national, but the rules for leak detection for underground piping and underground storage vary by jurisdiction. And Lee, in California, Lee, I think you see the most restrictive rules in the country for underground fuel storage.
Yeah, I mean, it's kind of a multi-layered thing. We're going to start with the NFPA stuff, and then maybe go down to the state level, and then down to even county and city. So unfortunately, there's not really any sort of centralized thing. There are going to be some things like in the state of California where we have the guidelines that are laid out by State Water Resources Control Board, AB Assembly Bill 2481, LG 113, that sort of thing. So, that's going to be statewide. But then even beyond that, it's going to depend on, for example, is it in San Francisco? They're very careful in San Francisco. LA, maybe a little bit more restrictive than the rest of the state in some ways. They have 60-gallon day tank rules, that sort of thing. No fuel pumps transfer pumps running supply pumps unless the generator engine is literally running. So each area has its own things, but there could
As
be
luck would have it, Preferred has people in most of the difficult jurisdictions.
yeah.
And we all know the national code. And really, when you want the final answer, call the fire marshal where the plant is located, because they're the ones with the red and the green tags that make all the difference.
Right.
That's really the best answer right there is, I'll get asked by engineers, are they going to allow this? Are they going to allow that? Well, we've seen them allow this before. We've seen them not allow it. I can't tell you, really got to talk to the fire marshal. They are the ultimate authority, and they can require things that are unwritten as well. So ultimately that is the best answer, really. But in answer to your question, I don't know of any national, centralized way of really looking at this. It'd be nice if they were. Maybe that's, a side business for all of us, right? Put it all together.
Before we continue on, I want to let everyone know, if you are having, it doesn't seem like we're having too many problems with the presentation as far as audio. I had 2 or 3 people ask me, and something that seemed to resolve it was just to reload it. But once again, we're not having too many problems with that. So if you're having an audio cutout, or the screen seems to be frozen, just reload the presentation, and it should fix any of the problems. That seems to be the fixer right now at the moment.
All right, let's go back to the presentation.
All right, I send in connection over to you.
We're always supposed to say, that's a really good question. But in this case, we've actually had really good questions. I'm not lying this time.
Because we have great attendees.
Okay, go ahead, Lee.
Okay. So the next thing we're really going to look at here is piping, and talk a little bit about double containment and sumps. Just on the right there, just what we're looking at really quick. That's a typical type of sump on the top there that you're going to see on top of a tank, or even mounted as a transition sump somewhere along the line for accessing the pipe underground. The photo in the middle there is basically that is actually a direct draw system, because I worked on this system. It has the pipes going overhead, but you'll see a little containment box in the top there, and that is what we call a tank top sump. Now, this particular one is indoors, so it's open, but the only way to provide secondary containment when you're penetrating a tank, especially if it's a double wall tank like this is to, by definition, have a single contained connection, because you need to thread those components into the top of the tank. So in the case of a double wall tank like this, we need to have that tank top sump, because it's in a jurisdiction that requires full secondary containment. Reason why you see other components outside of that little box is because they're not moving fuel. Those are just vent pipes and level sensors. So we're not moving fuel through those bungs. So the bungs are actually moving fuel. The fill and the supply and the return are contained inside that box, and that box has a little leak detector in it. So that way we know those points of single connection that are actually moving fuel through them are secondarily contained by that box and leak detector. So that's what you're looking at there. And that's an important thing, especially in jurisdictions like California, more stricter areas. More stricter is not correct. More strict areas. You're going to have some sort of tank top containment like that. If that tank were outdoors, then that containment area would have a lid, weather resistant cover for it. The bottom sump that you see there is a very common unit that you're going to see, or type that you're going to see on an underground storage tank system, and that's a vent transition sump. So on this front area that you see would probably be some penetrations from underground pipe, and that would be the buried area. That trench plate area that you see would be like a lid that you can lift up, and you can work on the the transition of the piping there. So what this is, the transition part of transition sump is transitioning from underground, usually something like poly pipe or fiberglass, to steel, so that you can take the steel above ground and run it out to your generator. So that transition of underground pipe to steel above ground pipe is usually what these are used for. It basically is a way to convert underground pipe to above ground pipe. It's commonly called a vent transition sump because this is what you need to vent an underground tank. This one having 3 connections is either 3 underground storage tanks, each one only needing 1 vent. It's unlikely. This is more likely a transition sump for maybe a vent and a supply and a return. But that is what you use to transition from below ground to above ground. I think as far as the text here, I've pretty much gone over that, with the exception that, well, you can go back for a second. The underground sumps, again, if it's a pressurized system, in a lot of jurisdictions, it's going to be hydrostatically monitored interstitial space. So if you look at the top photo there, you see that little sensor sticking up. That looks to me like a hydrostatic sensor. So what that is, it's at the top of the sump, and it's monitoring that top level, right? That's where the liquid level is. And if it falls, it'll set off an alarm. If it rises, it'll set off an alarm. So that's an example of a hydrostatically monitored tank there, or sump, excuse me. Make sure to spec and use approved boots for whatever type of sump you're using. There are all sorts of different variations out there. We can certainly make recommendations. They're going to work well for your project. Pipe sizing, headers, and branches. This is kind of an important part of the design process as well. If we have a situation where we have, let's say in this case, we've got 4 day tanks here. So we've got 4 generators that are all maybe the same size. We're going to have a larger header pipe to move all that fuel to all 4 simultaneously, but obviously only 1 generator will require a lot less fuel. So we're going to size the piping based on how much fuel do we need to move through this pipe header to all the tanks at the same time. But then each day tank coming off in a branch from that header can be smaller pipe diameter because we're moving less fuel to that 1 day tank. So when we assist with the pipe sizing, we're also going to be looking at the headers and branches. We're going to look at the main pipe and then all the little branches going off to the day tank. So we're going to give you multiple different pipe sizes. Reducing that branch size just makes it more easier to deal with, easier to install. The valves are smaller, etc. So we're going to look at sizing all of that accordingly. If you have a single generator attached to a transfer system with a tank, you're going to have your pipe header and your branches are going to, there is no branch, so it's going to be the same size all the way through. So hopefully that makes sense. Sometimes if we need to achieve a really high amount of fuel, say on an upper floor, and still adhering to code, like we've got a whole lineup of a lot of generators, sometimes we can use what's called an oversized header, meaning we may have a 2-inch pipe going up to a rooftop and then maybe feeding an 8-inch pipe that is the length of that room, and then next down again to a 2 or 3-inch. We can use those in situations where we're trying to provide a lot of fuel to a lot of generators, but we have a limitation as far as how many day tanks we can have or what size they're going to be, but require a high volume of fuel to be moved. So we will use, in this case, a flooded header. And this is not very common. I've only worked on it a couple of times myself in the past, but it is a possibility, but it also is very important to make sure that we have an active, complete conversation with whoever the jurisdictional authority is, and make sure that they're okay with approving that type of a system. If anybody wants more information on that system, I'm not going to go into it right now, but you can contact us and we can discuss that more with you.
Yeah, oversized headers are not allowed anymore in New York City. I think the largest fuel line you can have in a building in New York City is 2 inches. And the super short answer on pipe sizing is we like to keep our flows under 7 feet per second. The more exact answer is you Google preferred pump pipe sizing calculator, and you'll get to our pump and pipe sizing calculator that very quickly you can put in all your flows, select your pumps, select your pipe sizes, and it'll tell you exactly what your discharge pressure will be on the pumps. And you can get there by Googling preferred pump pipe sizing calculator.
Yeah, that's a good point. One of the reasons why we want to keep it under 7 or 8 feet per minute is if it goes too fast and we're shooting fuel into a tank too quickly, you know, the pipe diameter isn't large enough, that sort of thing. It could, if the velocity is too high, when it gets in the day tank, it may foam, and if it foams the fuel, you'll get funky readings from your level sensors potentially, and that sort of thing. You could swirl the fuel if it's a really small tank, that kind of thing. So we take a very close look at what Dave said as far as feet per second, fuel moving through the pipe, et cetera. So pipe sizing is crucial with making sure we're in those correct parameters. The supply piping suction side, when we're using gear pumps, we want to, of course, make sure that we limit the suction lift, as we discussed in the past. We like to limit that to 15 inches or less. It is possible to do more than that, but it starts making everybody uncomfortable. Typical piping friction loss is about 5 inches of mercury. This leaves about 10 inches for static lift, or approximately 12 feet of oil. So when we're talking about a larger tank, like a 12-foot diameter tank that's got a 3-foot bury depth, usually minimum, we start to get into an area where we really want to take a close look at it. And I'll call the factory engineers and talk to them about it and look at the drawings and everything, and get bigger brains than mine involved at that point a lot of times to go through it with the engineer. Suction piping, again, can be eliminated by using submersible pumps, which, as we've discussed, have different attributes and limitations, high flow, low head, etc. So, you know, again, it's going to be dependent on the particular situation. On the discharge side, of course, we want to use the flow switches on the discharge of the pumps, but sometimes we'll put them out at the day tanks, either instead of or in addition to. I prefer in addition to confirm that the transfer system is functioning properly. And if there's a piping problem, if we just have a flow switch on the discharge, then that doesn't mean that somebody didn't break the pipe out of the day tank. So it's, you know, it's a good consideration in some cases to, especially on long supply line systems, to have a flow switch at the day tank as well. One thing that I do see is that fuel loops are more common than are usually necessary. Dave touched on this before, and when he was talking about boiler systems with back pressure regulating valves, because you have to maintain sometimes up to 100 psi to supply a boiler loop. I see systems from time to time that are looped, that have a back pressure regulating valve, and typically on generator systems, they're just filling atmospheric day tanks. So there's not really a reason, unless you're using something like a flooded supply header, to loop the fuel lines and have a back pressure regulating valve. Generally, it's okay to just dead end the supply line at the end of the day tank lineup and have a totally separate and dedicated dead end return line coming back from the day tanks. That's your typical layout situation, and eliminates the back pressure regulating valve, and just simplifies the system. So
I see back pressure regulating valves called out at the end of supply headers for generators pretty often. And I think in the engineer's mind, they're thinking that they need that back pressure regulator there to pressurize the system so that all the day tanks get equal access to the fuel. But I've never actually seen a system that deadheaded that would starve one day tank if more than one day tank was calling for fuel.
yeah, if you have a really large system with, say 12 generators with a really big header pipe, I could see the first ones in line getting more fuel. But in that case, we're usually using flow restrictors at each day tank inlet to slow down the fuel so that they all get fuel at about the same rate. The added benefit of using flow restrictors on systems that have multiple generators is it also allows us to put smaller return pumps. Because the flow is restricted so much into the day tank, you can have a 3 GPM flow restrictor on every single one of those 12 day tanks. If you don't, you may be pushing, hundreds and hundreds of gallons per hour into a day tank, which means that if that one day tank inlet valve is open and all the other ones are closed, that day tank's going to get all that fuel from those big pumps for all those generators. In which case you have to have a huge return pump. If we use the flow restrictors, maybe a 3 GPM flow restrictor, then we can have a 5 GPM return pump instead of a 15 GPM return pump, right? So there's an ancillary benefit also to using the flow restrictors on those systems. So that was a really good point, Dave.
Lee, I feel like this is an area where NFPA code leaves a big gap, because I can't remember if it's NFPA 30 or 37, but it says that your overfill line has to be capable of more flow than your supply line, so that you're not restricting your overfill line and overfilling a tank that way. So in a gravity return system, it's very common that your return piping will be one size larger than your supply piping. And recently our New York City specialist told me that you are required to show your work when you're designing a gravity return system. They want to make sure you've done the calculation to make sure that you can return enough fuel by gravity. So the underlying requirement is that the return piping has to be able to flow more oil than the supply piping. In the case where you have an above ground storage tank and a day tank that's going to be below, they may both be on the same level, but the main storage tank may be 10-foot diameter, 12-foot diameter. The day tank's only going to be 4 feet high. You're not going to be able to gravity return. And in that case, you need a return pump to pump the oil back up to the above ground storage tank. And according to our interpretation of NFPA, that return pump has to be able to flow more oil than your supply piping. And when we have a lot of generators stacked up, we'll put a flow orifice into each flow manifold so that our return pumps don't get really huge. But if you go through NFPA 30 or NFPA 37, there is no mention of return pumps. Not yet. But there is a requirement that the return be able to move more oil than the supply.
Yeah, and I think, with prudent design, let's say you've got a 3-inch supply line, or, say a 3-inch supply header. One size up, I could do a 3.5-inch, return pipe. But if I've got 12 generators, and I'm pumping this tremendous rate of fuel to these 12 different generators, I'm not going to feel comfortable with that scenario without return pumps. I'm going to potentially overwhelm that gravity return, or in the case of using return pumps. So every scenario needs to individually be looked at. I think it's really good that they're requiring the people in New York to show their work, because you could have one generator or you could have 15, and that's going to make a big difference on the one size up rule. I would definitely be any situation like that. I would absolutely be using return pumps. There's no question. And
Yeah, but if you're
very
go
very
looking through an
slower.
FBA, you're not going to find a mention of return pumps.
Yeah,
So,
yeah, it's interesting.
spoiler.
Yeah,
I think we talked about this whole slide.
pretty much. And this one as well, for the most part. Again, I mean, flow restrictors can save you a lot of money and a lot of space on not having huge return pumps on a multi-generator system, especially multi-generator system. Flow restrictors will save a lot of space and effort and cost.
We talked about most of this when we did the flow schematics.
Yes. Flow versus consumption. Just make sure that you're sizing.
You talked about level bouncing.
Yeah. The main thing here is just make sure that you're sizing for consumption when your generator is pulling and returning between the day tank, and size for flow when you're returning fuel from the generators directly to the main tank. And that's
and considering the generator fuel pumps can be 3 to 4 times consumption, it can get you into some very large supply pumps if you return directly to the main tank. So in most hot climates, we're going to do level bouncing rather than return directly to the main tank. And the only alternative, the only exception I can see to that is Los Angeles, where you're limited to 60-gallon day tanks.
Yeah. We talked about fuel velocity as well, to try and keep it between 3 and 8 feet per second. So we're trying to be not all that repetitive here.
All right, this is all new material here.
Yes. So do you want to talk about the valve types, or?
Sure. Lee's talked a little bit about foot valves. They go at the bottom of the main tanks and sometimes in the day tanks. And the foot valve is like a check valve in that it keeps oil from flowing backwards and losing prime in a suction system. And they come in a single poppet and a double poppet configuration. And when you've got plenty of pump suction, we'll use a double poppet foot valve. The overfill prevention valve, Preferred makes 2 types, one for pump tanks and then one for gravity tanks. And essentially, these are toilet float valves. They're exactly like the valve in your toilet that when the water level gets up to a certain point, it shuts off the oil. And these are physically installed in the tank and they'll shut the oil off usually around the 95% level. But in most jurisdictions, alarms will be going off at the 90% level. And a responsible truck driver, if he gets to 90% and the customer wants more fuel, he's going to be going very slowly and watching it very closely to make sure he doesn't overfill. But in fact, the one on the left really looks a lot like the newer toilet float valves. There's a little float assembly down there that connects to a linkage that closes off the line so that when you get up to that level, no more oil in the tank. The next component is the anti-siphon valve. And we talked a little bit about that in Lee's slide with above ground storage tanks. And my background is boilers. And I didn't really care where the oil came from on a boiler system until I started working at Preferred. And I had a difficult time getting my head around what an anti-siphon valve actually does. But it's similar to a check valve, and the springs come in 4 foot, 5 foot, 10 foot, and 20 foot, depending upon how much oil is in the main tank or what the level of oil is compared to the lowest point in your piping system or where the pumps are. And the idea is that if you size the spring properly, the siphon effect won't have enough differential pressure across the valve to open the valve, but the pump will. So if you get a break in the line or somebody doesn't tighten up a union, the siphoning effect or that differential pressure won't open the valve, but the pump, being able to deliver at least 15 inches of mercury, will be able to open the valve and allow oil to flow. The basic valve you're going to see in most fuel handling systems is a solenoid valve. You're going to see them on day tank fill manifolds on at least 90% of your day tanks, and you're going to see them on tank select valves. We try to get people to specify motorized valves for tank select valves because they're really just they're a ball valve with a motorized actuator on them. The ball valves are more likely to shut off tight than a solenoid valve. If you get a little bit of dirt, debris, or gunk in a solenoid valve, it can cause the solenoid valve to hang up and not close completely. Whereas a ball valve will be able to close against a little bit of dirt or grime or grit. Also, motorized valves are available with end switches, so we can make sure the valves are in the right position before we energize the pump. On the fill manifolds, we're always going to put a 3-valve manifold around the solenoid valve or the motorized valve so that we have a way of manually filling the day tank. And you know, your fuel system really should be designed for worst case. You know, if something goes wrong with your control system is completely sideways, you can open up a flow manifold and you can put a pump in hand, and that'll allow you to fill a day tank in an emergency. And I mentioned earlier that we don't rely on our microprocessors to do overfill prevention. That's hardwired for us, so that even if there is a problem with the processor, the solenoid valves are hardwired through the high limit switches on the day tanks and the main tanks, so that you can't overfill them, even when you have pumps in hand. You need to be careful where you specify check valves. You're going to see them on our duplex pump sets. You're going to see them in return piping. Just anywhere you can't have the flow going backwards. Preferred makes a couple of different types of fire safety valves. The one on the left is a fusimatic valve, and the one on the right is a 110 lever gate valve. The 110 lever gate valve is just a spring-loaded gate valve, and you manually turn that lever to open the valve, and then you tie that valve open with a cable, and the cable has I forget the term for it, but it has a eutectic alloy in there. And
fusible link.
Fusible link. Thank you, Lee. That's why we have 2 people on these presentations, in case one has a brain freeze. So the fusible link melts at, I think, 165 degrees. So if the fusible link detects high temperature, the fusible link breaks and the spring closes the valve. You can also get that valve with a limit switch to tell you when the valve is tripped and when it's open. And that can talk to the fire controls in the building. We sell a lot of these in New York City. In New York City, you'll see a fire safety valve at the fuel entrance to the building. And then the cable has to be run across each of the boilers. So you'll see the cable run kind of perpendicular to the boilers with a fusible link above each of the burners. And that way, if you have a one-box fire or something, the fusible link melts and you shut off the fire, or you shut off the oil at the entrance to the building. But you can put these anywhere you want, really. Back pressure regulating valves, we don't often need them in generator fueling systems, but we will typically always have them in a boiler loop. And the back pressure regulating valve is sort of the opposite of a traditional PRV. A PRV senses and modulates to maintain downstream pressure, whereas a back pressure regulating valve senses upstream pressure and allows fuel to go through the valve to maintain upstream pressure. So they're a little bit like a relief valve, but a relief valve is just open close over pressure prevention, and a back pressure regulating valve will modulate, and they modulate to maintain upstream pressure. So you put it at the end of your boiler loop, and the output of that valve really becomes the beginning of your fuel oil return line. And The pressure requirements for boilers can be difficult to figure out because some boilers have onboard pumps and some don't. And the requirements for those pumps are different from manufacturer to manufacturer. And like the pumps on generators, the pumps on a boiler can flow a lot more than boiler high fire consumption. So if you're not sure, just let us know. We know a lot of the burner manufacturers. We're a burner manufacturer, and we sell controls to all the burner manufacturers. So, we usually know somebody we can call. Another thing that's difficult too with new boiler projects is an engineer will specify a particular boiler, and that boiler might have onboard pumps on it. And if that's the case, we'll size the back pressure regulating valve and the fuel system for, maybe 3 to 5 psi, and that's the way the system is designed. But in many cases, the boiler that ends up on the job is not the one specified. So someone may take exception and you'll end up with boilers on the job that don't have onboard pumps. And in that case, the consumption may be lower because we only have to size for consumption, but the pressure requirement can be much higher. It could be usually 100 psi, and in rare cases, 150 psi. Vacuum breakers, pretty self-explanatory. Pressure relief valves are like a back pressure regulating valve. They're just open close. And they're called a pop-off valve because when they go, they make a very audible pop. And they pop when they open, they pop when they close. So sometimes one will chatter and it's just pop, 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 pop. They are not to be used for regulating pressure. They're only to be used for over pressure prevention. And then pressure reducing valves, the opposite of a back pressure regulating valve, and much more common. They sense downstream pressure and modulate to maintain downstream pressure. Sometimes we do systems that have both boilers and generators on them, and we might have a mix of back pressure regulating valves and pressure reducing valves. And when you're doing a burner system, you need a pressure regulating valve or pressure reducing valve on each burner because the header pressure may vary a little bit depending on how many burners are running and what firing rate those burners are at. And each boiler needs its own pressure regulating valve to compensate for that. Otherwise, you'll get combustion that could be a little richer or leaner than what you anticipated. We did this slide. I think I talked about most of this already. Most common is solenoid valves, but we like motorized valves when we can specify them because they're tight shut off and we get proof of open and proof of closure switches.
Yeah, and for those of you still hanging in there, we appreciate it. A lot of this stuff will go a little bit quicker because we've touched on a lot of it, so it should go pretty quick.
Yeah, and I think we've talked about all the different types of spill containment and leak detection. You've got float switches, you've got the HDA2s that do discriminating leak detection. They use a combination of an optical sensor and a conductivity sensor to tell you whether the leak detected is oil or water. And then in California, Lee does a lot of vacuum leak detection systems where you pull a vacuum on the interstitial of the tank and the double wall piping, and then any loss of vacuum is interpreted as a leak, and Preferred has a monitoring system for those. We also do cable leak detection in sort of a partnership with Permapipe, where we've put their PAL8T controller in our pump control system. And these systems are pretty cool because if you get a leak, it takes a map of your system and it can pinpoint exactly where the leak is. And then it maps that. And then every once in a while, it'll refresh that map so that it'll tell you, you may have had a point leak at 137 feet. The next time it maps, it might tell you that your leak is now 135 to 139 feet. So not only does it tell you where to dig, it can also tell you how bad your leak is by telling you, what the limits of it are. And It's a cool system. I mean, it's been around forever, but now you can get it incorporated into your preferred pump controls as well. Another very common question is, how many vents do I need and where can I run them? And that's another question for the fire marshal. Lee, you're pretty comfortable with that question in California, and it's different in San Francisco and Los Angeles. But if I were designing a system in one of those areas or New York City, I think that's something that I would get the fire marshal to okay before we start cutting holes in buildings. Do you agree?
Yeah, yeah.
I mean, they even have rules on where you can terminate the vents. They can't be close to air intakes, and they can't be close to windows.
Yeah, they need to be 12 feet above local grade and yeah, away from any kind of air venting, even in or out, and have to be away from windows as well, whether they operate or not. So that's something that we look at when we want to look at the projects.
Okay, so the different types of pump controls. The older way of doing this was with relay-based systems, and relays can be very, very reliable and repeatable. The biggest thing that can take down a relay system is that the relays can be pulled out of their sockets. And you can get an operator or a facility person that'll pull a relay out of its socket because it's buzzing, and now you've changed the logic in the system. I'm old enough to remember when we used to do flame safeguard systems with relays, and they were big, massive panels, and you couldn't change any of the logic. And what we find a lot is that we're told to design the pump controls around a certain number, a certain type of inputs and outputs, and then when the system gets out into the field, we find that oh, there's another leak detector here that we didn't know about, or oh, we thought we were going to have manual tank select valves, but somebody's provided automatic tank select valves. So it's very common for us to have to do a program change. So for that reason, preferred's almost 100% now microprocessor controls, and they're programmable, because more often than not, it seems like our fuel oil startups start with a program change, because the IO in the field is a little bit different than what we were told. And by the way, this lower right-hand picture, that green board in the top left is the PermaPipe or PermaAlert PAL-AT board. They fit it right into our pump set enclosure. And that processor on the right is the preferred FSC processor that we use on virtually all of our fuel systems. And with microprocessor controls, you can get any sequence that you want. We have our sequences, and we feel our sequences are the safest because we literally do hundreds of these fuel systems every year. And most of the people in our engineering group in fuel oil, all the engineers but one have worked for the company at least 25 years. So they've seen thousands of fuel control systems. And it's a little bit like when I went to my first parent band trip meeting, where the teacher said, some of these rules are going to seem really bizarre, but believe me, there's a reason for every one of these rules. So when I came over from doing boiler controls to seeing preferred pump controls, some of the things that we did seemed a little bizarre. It turns out there's a very good reason why we do them the way we do them. And the short answer is the other way isn't as reliable. So I can give you a bunch of examples of that, but we're running out of time. We're also open to custom sequences. If it's not a safety related thing, we can custom program a fuel system to work the way you want it to work. If you ask us to do something that we think is not safe, we're going to push back pretty hard. So every component in a fuel system is a safety device. And, you know, not only have we thought out the pump controls, we've also thought out all the different failure modes. You know, so for instance, all of our leak detectors are made in the down position. So we don't have an alarm that goes off. We don't have an alarm that goes off when we detect a leak. We have a contact that continuously tells us we don't have a leak. And if we ever lose that contact, or we lose that voltage on the digital input, then the alarms go off and we say that we have a leak. And the reason for that is in an energized to alarm type circuit, any kind of failure that de-energizes that circuit, you won't know if you get a leak. Let's say you have an energized to alarm system and you blow a fuse, or a wire isn't tightened down in a terminal block. You're going to have no voltage on the digital input, and that's normal. And then when you get a leak and that contact closes, you're still going to have no voltage on that terminal, and you're not going to know you had a leak. So the way the Preferred does most of these safety devices is we are continuously proving the normal condition through a normally closed contact. We don't wait for an upset condition to energize an alarm circuit, if that makes sense to you. We talked about this. We talked about day tank capacity. You know what, Michael, we're down to 15 minutes left. Let's switch over to questions from the chat, if we can, please.
Sure. Absolutely.
Yeah, we've gone over a lot of this, but this is really the end anyway. So, you know, we're pretty much ready for questions at this point.
All right, let's start it off. Just figure out where we left off. Presentation still on? Yes. Did we go over the way, sorry,
one of the slides that we skipped over was cold climates. We talked a lot about hot climates. If you're doing a fueling system in a cold climate, we have ways of heating the fuel. We can add a thermostat controlled heater to our pump sets, and you can heat trace. If you're going to do a fuel system in a cold climate, especially where you have above ground tanks and exposed piping, let us know. We can design for that.
Perfect. All right. A question we have comes. It says, does biodiesel tank for boilers handle fuel polishing differently?
You've got to be a little bit careful with your material selection with biodiesel. Rubber seals don't do well with biodiesel. So if we're going to do a polisher for B20 or B100 or bioresidual oil, we'll just make sure that we're not using any rubber seals or any other components that'll get eaten up. I did a paper on this a couple of years ago for IDEA, International District Energy Association, and I did a ton of research, and what I found is that even more than diesel fuel, biodiesel has a tendency to collect water. And you know, tanks are vented, so they're vented to atmosphere. So if the tank gets below the dew point where you're at, it's going to condense water inside the tank. And biodiesel is worse at attracting fuel than number 2 oil. But the filtration system, you know, any good filtration system will have a canister filter in it or a coalescing filter that'll knock the water out and get the sludge out as well. And we can build those systems with a large water holding tank to store all this water that we pull out of the tank, because you can't just put it down the drain anymore. But yeah, biodiesel needs fuel polishing even more so than fossil diesel, and our filtration systems can handle it.
You know, one thing I just wanted to throw in there too, if you're in a situation where you're concerned about the especially condensation, contaminating the fuel a little bit quicker with biofuels, especially on higher concentration biofuels, is consider using cylindrical tanks for bulk storage, because they, rectangular tank, you always have 100% of the surface area of the ceiling of the tank available for condensation and dripping. But if you have a cylindrical tank and you keep it relatively full, up at 90%, you have a lot less tank area internally to drip.
Yeah, another thing we've found too is that the sulfur in diesel fuel is a natural biocide. So when you take the sulfur out of the fuel, like we've done now with ultra low sulfur diesel, ultra low sulfur diesel is now a better fuel or a better food for bacteria than traditional diesel. So ultra low sulfur diesel, it's even more important to specify a polisher, especially in humid locations like the Texas Gulf Coast, Florida, where it can be cool and humid and tanks just really, really condense.
Great. Next question is, what's the largest volume fuel oil you've seen installed in a building in the last few years? So that seems like just a general question.
The largest one I've seen is the data center we're not supposed to talk about. It had 10, 40,000 gallon tanks.
Yeah.
And gigantic belly tanks.
Those were above ground storage tanks too, so they're huge.
They were massive and all lined up.
I have not worked in a few years on any of these, but I've seen, and I'm sure Dave, you've seen larger ones too, like in the 600,000 and 800,000 gallon range. But those are all underground jobs as well.
Great. Next question is, do you have Revit files for your equipment, and do you know if PermaPipe has as well?
What kind of files?
We have Revit. We have AutoCAD drawings and SolidWorks drawings for virtually everything. We have Revit files for some of our more common equipment. And as luck would have it, Michael's actually in charge of doing our Revit conversions. So if we need something in Revit format, Michael's the guy that'll take it from AutoCAD or SolidWorks and put it into Revit for you.
Right. Exactly.
I'm sorry, I don't know if PermaPipe has that available. And I apologize. Don't send me a nasty email.
Especially if you're from PermaPipe.
That's what I'm expecting, is a nasty email from PermaPipe saying, why haven't you read every page of our website?
How difficult is it to replace the PermaPipe once it gets soaked in fuel?
Yeah, so most of the leak detection cable is single use. When you build the PermaPipe system up, the components include fittings for drawing the cable. So it's relatively easy to draw the cable through the pipe, and they recommend that you put a pull box. Man, I'm going from memory. Please don't send me an angry email. I thought they said that the pull boxes needed to be 500 feet, at least within 400 or 500 feet, which I thought was amazing. If I didn't know any better, I would want to put a pull box every 50 feet. But the way their pipe is designed, you don't need as many pull boxes as I thought you would.
So it's zoned in a way, is really what you're saying, is you're only probably replacing a zone up to 500 feet at a time.
Yeah, because you can do a point leak detector as well. So when you map out the system, you can tell it where you have a float. So if you have a float in a sump at just say 250 feet, the cable's going to terminate at 250 feet, and if it detects a break right there, then it's going to say this detected a leak in that sump, and then you can continue the cable on the other side of that.
All right, next question is, how do you determine the head value for an anti-siphon valve?
Are you going to take that, or you want me to take it?
Sure. You look at the distance between the top of your main storage tank and really the lowest point in your fuel distribution system, which is usually the pumps. And short answer is, if I have a 10-foot tank, we're going to use a 10-foot spring. And that seems to be our most common.
Got it. Next, sorry. Next one is it ever okay to tie the relief line back to the pump suction?
We do that sometimes in situations like where we're using a booster pump to push fuel up to a rooftop. Other than that, that would be the only reason I would want to use it, but there may be other applications. Dave, maybe you know of others.
Well, you've got to be a little bit careful when you do that, because as the oil moves through the pumps, it's going to pick up a little bit of heat. So if we're looping a small amount of oil around and around and around, that oil can get pretty hot. So we have to be careful in that situation. We'd rather see the oil go back to the main tank. And you know, I started out in boilers. Whether we were firing number 6 oil or number 2 oil, it was always a good idea to start the pumps and start oil circulating well before you tried to light off the boiler, because if you had a little bit of water in the oil, or if you had some gunk in the oil, you wanted to move the oil around so that to give the strainers a chance to catch the gunk, and you wanted to mix up the water, because a burner will burn a little bit of water in the fuel if it's evenly mixed. What you don't want is slugs of water hitting the burner all at one time. That makes for interesting combustion that you don't want to stand too close to.
Yeah, the short answer is, you know, really, it's always best to tie it into the return line, because that's really where it's supposed to go. If you have a situation like a boosted remote fill where you only have a fill line and no return line, that kind of thing, you're looping it through, you know, a very short distance, like Dave was talking about. Generally, though, there's going to be somebody standing there, a fill operator, and is going to say, hey, there's something wrong. You know, there's a valve closed. I'm pushing against a closed valve. The flow switch won't make, so it'll probably shut the pumps down anyway. So under certain circumstances, it's okay, but I would avoid it as much as possible. Is that a good way of putting it?
Yeah, it's not a practice we recommend.
Yeah.
All right, next question is it better, what is better to use, an anti-siphon valve or a solenoid valve? I guess what do you each recommend?
Anti-siphon, unless there's a reason why you need to use a normally closed solenoid valve, like in the case of a direct draw system. Otherwise, I would prefer to use an anti-siphon valve.
Good. Next, what are the pros and cons of using separate pump set design versus having the pump set integrated on the day tank?
I don't like to see supply pumps on the day tanks, because if you really think hard about it, we can't pull oil. All we can do is push oil. And when we're pulling oil, what we're essentially doing is we're evacuating the suction side of the piping, and atmospheric pressure on the tank on the oil is filling that line. So we're really kind of limited to atmospheric pressure as our prime mover on the suction side of a pump set. And that's why the preferred pump and pipe sizing web page asks you for your elevation, because higher elevations, there's less atmospheric pressure to move that oil. And I've had engineers who will use the pump and pipe sizing program and say, you know, look, I got 250 feet of suction line and it's exactly 15 inches of mercury, so I'm going to be good. Well, that's ideal conditions. You know, bear in mind, if you get a leak in any of that piping, you could lose prime. And a lot of piping systems that you pressure test won't show a leak, but if you vacuum test them, they will show a leak. So we'd like to see we'd always like to see the transfer pumps as close to the main tank as possible so that we can push the fuel rather than pull it. Also, there's a practical consideration. We can't put really large pumps on really small day tanks. There just isn't enough room on top. And I've seen other people make supply pumps on day tanks and just hang them off the side. We don't do that. We put them on the top of the day tank so that the pump sets are covered by the rupture basin on the day tank. That way, if you get a leak, it's captured by the rupture basin, where you've got a leak detector to tells you you have a problem. So we advocate strongly for return pumps on day tanks because that's pushing oil back through the return. We make them, but we would prefer to not put supply pumps on day tanks if we can.
Very good.
Yeah, I would just add one thing, and that is the pumps are really built to, as sort of as Dave mentioned, they're built to push fuel, not pull it. They are self-priming, but they're not designed to burp air and pull fuel. They're really designed to have fuel and push it. So more efficient.
Guys, it's straight up the top of the hour. We've gone 3 hours, and I just have an immense amount of respect for the attendees that sat through a 3-hour marathon. Although if I were running the marathon, it'd be a lot more than 3 hours. I want to thank everybody involved. I don't see why, I mean, I got nowhere to go. I don't see why we can't continue with questions and answers.
Yeah, we've still got, it looks like 78 people, right? So
yeah.
Okay,
Right.
Again, thank you for attending, everybody. If you want a copy of the presentation, just email me or Lee or Michael. If you have questions about a specific project, Lee or I will try and help you. If you're someplace like New York or one of the other special jurisdictions, we'll hand you off to the preferred person in that area who's an expert on your regulations, and we'll keep going.
Right. All right. Next question is, how do you suggest adjusting the anti-siphon to vary the resistance as fuel level changes versus using a solenoid? The anti-siphon valves are static resistance set on the spring and works best at set head pressure setting and don't work as the main tank varies more than a couple feet. So I can read that again if you want me to.
I understand it. Did you understand that, Dave? That's
I think I get the gist of the question.
You can take it. I think that's a good question. It's the first time I've ever gotten that specific question, but you can take it if you want, Dave.
I'm gonna wuss out and listen to your answer first, and see if it's the same as my answer.
Oh boy.
Yours is probably better because I don't have a whole lot of answer to that aside from that's just kind of the margin of error that we're dealing with when we're dealing with static springs with a static strength to them. But that is an excellent point. I think that there's a range of acceptable acceptable range of spring pressure in there, so that when we fire the pumps, they can easily overcome the spring and we're okay. But we're mostly concerned with the maximum amount of fuel and that spring being just enough to hold it back.
Yeah, and I think where this question is going is if you size the anti-siphon valve for a completely full, let's say 10-foot diameter above ground storage tank, the anti-siphon valve still works if you have 7 feet of fuel or 6 feet of fuel or 2 feet of fuel in the tank. You're still not going to open that spring up with hydrostatic pressure.
And the pump will still be plenty strong enough to pull it open either way.
Right, the pumps will still open it up. I suppose if you started pushing fuel up the vent, you could get enough differential pressure that you overcome the spring and open up the anti-siphon valve. So if you're trying really hard to overfill a main tank, the anti-siphon valve theoretically seems like the anti-siphon valve could open, and then
But you know, if you've got a
There's
6-foot
nowhere for
tank,
the fuel to go.
if you got a 6-foot tank, then you only have probably a 6-foot vent on top of there, and it's probably only, you know, a couple inches big, so it's probably not going to
Yeah. And
do
if
too much.
nothing is calling for fuel, then there's no place for that oil to go. So it's not even going to free flow through the pumps either.
Interesting question, though.
Nobody's ever asked that before.
Yeah, me neither.
Okay.
I think that guy
Next
almost gets a jacket.
Next question. Typically the engine has its own fuel filters. Do you recommend a strainer or filter in the fuel oil piping? And if so, where does it go in the piping?
Okay, this is a subject that I'm really passionate about. Occasionally, I will see somebody design fuel filtration in line with the transfer pumps. And that's a really bad idea because it's common to have a fuel filter on the engine, and that's great. But typically our transfer pumps supply more than one generator. And I've seen people put filtration canisters either on the suction side or the discharge side of the pumps. And the problem is if you clog that filter, now your day tanks get no fuel. So we'll put simplex strainers in our duplex pump systems, and if you clog one strainer, you can move over to the other side. Or we'll do a duplex basket strainer where if you fill up one basket, you can switch over to the other on the fly. If you put one canister in a fuel system and that canister fills up, then you've cut off fuel to your day tanks. I saw a system that was even worse that had canister filters and then a 3-valve bypass around it. Well, what's going to happen in the field if those canisters fill up and aren't moving any fuel? The plant personnel might be tempted to open up that 3-valve bypass, and now they're sending dirty fuel right to the generator. And if the dirty fuel hits the fuel injectors in the generator's down until you can call a technician. So we will do a little bit of straining in the transfer fuel system, either with a duplex basket strainer or 2 simplex strainers. We won't do the polishing in the fuel transfer system. The fuel polishers will be on a completely separate loop. You know, our filtration systems or our polishers have their own suction lines and usually their own return lines, or they may dump into the common fuel or return line. But the thing is, you want your filtration to be on its own loop. That way, if worse comes to worse, that you get a bad batch of fuel, and you get so much junk out of your fuel that it clogs your strainers, then your filtration system is down until you replace the strainers, but you haven't shut down your whole fuel supply system.
I'm really glad that you answered that. That's a way better answer I would have given. But I did want to add one thing, and that is, for example, we have a distributor who shall remain nameless because they're probably on this webinar right now, but who makes it a habit of always equipping pump sets with the duplex strainer option for exactly that reason, that you can switch on the fly, and you don't have to switch lead lag pumps or anything like that. And pretty much every single pump set that is ordered from this particular distributor has that DP dual strainer option for that reason. It's
They're
an
awesome.
excellent idea.
You can dump one basket while you run on the other, and then you can turn over and dump that basket. It's quick.
Yeah.
All right, next question. Do you know the day tank size limits for New York? So I guess in general.
God, I hope John Haber isn't listening. I thought New York City was the same as national, that they limited it at 660 gallons. What is different about New York City day tanks is that they need to be made to 25 PSI design instead of 5 PSI design because They more often go in basements in New York City, and you may have to run the vent a lot higher.
Got it.
I don't want to give any misinformation, but I do seem to remember something also that is different out there in New York, that when you start going up the building, you may have restrictions on size. Your size may decrease. Is that right?
I think this guy gets a jacket.
Well, I think if John Haber was here, we got this.
Yeah.
Oh, yeah.
John or Rob or anybody in our ACS office, they'll probably be sending me an angry email.
He's also left the presentation, so we should be okay.
Angry emails I'm going to get from Permapipe.
All right, next question. Some generators also don't like to run the engine fuel lines overhead if they are remote in the generator room rather than right next to the generator. So I guess he's just commenting that some generators don't like to run the fuel lines overhead. I'm
not just saying this, that's a really good question. Anytime you're doing a suction line, you want to avoid up and overs. And the reason is you can use the preferred pump and pipe sizing calculator, and it may say that the suction at your transfer pump or the suction at your generator fuel pump, which is even more sensitive because they can typically only do 5 or 6 inches of suction, you may be okay. But if you're taking credit for the hydrostatic pressure of the oil on the downstream side of that up and over, you got to bear in mind at the top of that up and over, you're going to have more suction. And we've seen engineers design systems with up and overs that are so tall that we would be vaporizing the diesel fuel because there's so much vacuum at the top of that up and over. So you've got to be really careful not to design up and overs in your suction line.
Yeah, and this individual who asked this question may have noticed in the one of the slides I was talking about, I was referring to the direct draw system and the picture of the tank with the little sump on the top. They may have noticed that that was an up and over, and I won't say what site that was, but I will say that we had originally designed that with the piping going to and from the generator between the tank and the generator on the floor with ramped, with ramps over it. And when I showed up on site with the technician to see the system in person when it was finished, we saw that it was up and over done by the contractor. And I'll be honest with you, I was like really not happy and was very concerned that we would have problems with that because it's not a very large generator in that room. However, I will say that it did work. They primed it and it worked, and it's worked fine ever since. But I understand the concern about that. I was very concerned on that very one that we saw. Anyway,
yeah.
I
had a hospital project years ago, big hospital, new construction, and they had a 25-foot up and over between the above ground storage tanks and where they wanted to put our transfer pumps. And I had a feeling this wasn't going to work. I ran it through the preferred pump and pipe sizing program, and I got all kinds of error messages saying, this is not likely to work. I went to the head of our fuel oil engineering department, and he agreed that this is not going to work. And we had to fight tooth and nail to get them to reroute that piping. And we tried to point out that it's not us. It's not us being difficult. This is high school physics. And they ended up getting some kind of machine that bored holes through a concrete walkway to reroute the pipe when we finally convinced them that they don't get a pass on high school physics.
I wish I. Oh man. Next question.
Oh yeah, we beat that last one to death.
Yeah, nice job. No code for that guy. When your pump set is being used as a transfer pump, pumping fuel from a truck up to a roof belly tank, This system does not have a return line, and I read that the relief valve can be piped to the inlet of the pumps. Question 1 is this true? Second question is there concerns of the key or the fuel overheating if the pump keeps running? I think we've kind of already talked about this subject.
This is Lee's area of expertise.
We've gone over this. Yeah, I mean, Dave brought up the fact that looping the fuel through a short stretch like that could overheat it quickly. I would say that circumstance is probably the only one that I would be somewhat comfortable with, in only because we don't have a choice, because there is no return line, and only also because somebody is standing right there, is required to stand right there and operate the fill. So when they see that there's a no flow condition, they should shut the system down. The system's going to shut down anyway because of the no flow situation. It's going to time out. And like I said, you know, it's attended. Somebody's right there. And you know, a fill box situation like that is a temporary operation anyway. It's not automated. It's always overseen. So, I mean, it's not ideal, but I'm okay with it in that situation. Otherwise, I'm not comfortable with it, unless you give me another scenario that is okay, which I haven't seen yet. Is that kind of your take, Dave?
Yeah, and I'm really impressed with the professionalism of the truck drivers that I see, the fuel startups that I've done. You know, I kind of envision these people, you know, they go and they start the pump and they wander away and go have a cigarette. No, they're good about standing there and watching, keeping an eye on things. I've never really run into a delivery driver that I thought didn't behave pretty responsibly, you know?
Yeah.
Okay, next one is, if you have a unit mounted air cooled radiator and it includes fluid cooled, sorry, this seems to be worded. Let me try to figure this out. And it includes fluid cooling, is day tank overheating still a concern? So if you have a unit mounted air cooled radiator and it includes fluid cooling, is day tank overheating still a concern?
What they're talking about is an engine mounted radiator air cooler, and I think those are a really good idea to specify with the engine, because it definitely will knock down the temperature of the oil going back to the day tank.
Most of them are included if you're in a situation where you have a huge day tank and you're in the desert or something like that. You can also always optionally add an auxiliary fuel oil cooler to a day tank that's not connected to the generator. So that's a secondary option as well.
I just saw those specified for a job in Chicago, which I thought was kind of overkill, because Chicago will get to 100 degrees maybe 1 or 2 days a year. But, you know, sometimes the person specifying the fuel system is not the person specifying the generator. So you may get stuck with a generator that doesn't have an engine oil cooler on it. Although I think that's a great option if you can get it on the generator.
Great. Next question, is there a situation where the piping needs to be heat traced?
Yeah, we actually skipped those slides. In cold climates, what we can do is we can put together what we call a thermopump system, which is basically a duplex fuel transfer system with a thermostatic controlled electric heater. And I think it works off of either air temperature or oil temperature. And we'll have a big electric heater kick in and add some temperature to the oil. And you can run that system whether you have a call for fuel or not. We can just sit there and recirculate oil and warm up the oil in the main tank. It depends on what kind of design temperature that you're dealing with. So if it's not going to get terribly cold, you can get away with just a thermopump. If it's very cold and you've got a lot of above ground piping exposed to the cold, then you might want to insulate that pipe and or heat trace it as well. Another option is just look at your winter blend. there's actually a big project going on right now where they're rebuilding the McMurdo station in Antarctica, and we're supplying some of the fuel handling equipment there, and it's unheated. And when I got the inquiry for this a couple of years ago, I kind of put a stop to it and sent in an RFI saying, I think an oil system ought to be heated in Antarctica. And eventually I got an engineer to reply that they burn a very special winter blend that's good to minus 40 degrees F. And they don't heat any of their diesel because they get this super winter blend. So winter blends are available to handle temperatures in Antarctica. So they ought to be available just about every place else. Or there's just a whole range of things that we can do with a thermal pump system, with electric heat tracing, with insulation. We haven't done this yet, but Lee's been advocating for it for years. Lee wants us to add an electric heater to our filtration systems. And then if it gets cold, you just run your filtration system and it adds temperature to your oil separate from your transfer pumps. We haven't built one yet, but eventually I'm sure we will.
I'm kind of glad you brought that up, because I was going to add that, you know, again, it is with a lot of these systems, kind of depends on the particular application and the particular system layout. I am working on a confidential data center project right now that is in a colder Western state. And what we're going to do there is most of the piping components are actually indoors, but the storage tanks themselves are above ground and they're outside. They're just outside the building. So there's very short pipe run that goes right off the tank and right into the building. What we're doing in this case is, since most of the piping is indoors, it's all double contained. We're actually using polishers outdoors, and we tried to put the heaters inside the enclosures, the filtration enclosures. We decided to put them in a separate housing outside because of their size. They're just, these particular ones were too big. So what we're doing in this case is we've got an AST and it's submersible pumps. So we don't have gear pumps on this. So we're relying on the filtration unit to activate on a filtration schedule and or activate on a thermal, you know, low temperature signal. And we're actually using an inline heater, and it's just a sort of a bonus that heated fuel will just circulate in the tank to maintain a minimum temperature in the tank. It's just a bonus that it gets polished when it happens. So we are actually deploying that, Dave. It's just not built into the filtration, assuming that we, you know, build the project.
Okay, next question. How do you handle day tank overflows that can't have valves installed by code?
Read that again?
How do you handle day tank overflows that can't handle valves installed, or that can't have valves installed by code? So it sounds like he's saying, how do you handle day tank overflows that can't have valves installed by codes? I'm kind of confused by the question myself.
Yeah,
well, an overflow won't have any valves. So an overflow return, I think what the question is how do we design a return system that's overflow when you're not allowed to have any valves? And the answer is, if it's an overflow system, we won't have any valves in the return line. There are no foot valves or anything like that. Just the fuel overflows from the day tank into the overflow system and just runs into, normally, most often, a UST.
Yeah, so in a gravity return, we're not going to have any valves, but in a pumped return, we've got to have a check valve. And if there's multiple main tanks, we've got to have tank select valves. I think that's an area where NFPA hasn't really caught up with practice.
Maybe.
If that person would please email Michael or I, we'll start an email dialogue and make sure we understand that question.
Drill down a little bit more.
Sure.
Yeah.
Okay. Next question is, discuss whether above ground fuel oil piping installed outdoors needs to be insulated. But I think we kind of covered this.
Yeah, I think we covered that pretty well.
Another thing you can do is paint it a color. You know, if it's a hot environment, you can paint it silver or yellow or white or something like that. That can help keep the temperature down.
Right. Will thermal pressure buildup between a foot valve and a gear pump be relieved by the P relief valve on the pump discharge pipe? So the pressure relief valve on the pump discharge pipe.
That's assuming that you've got a pressure trap beyond the pump discharge. So that would mean you'd have some sort of closed solenoid valve, like an inlet valve or something, and that you've got that you have a pressure trap.
Okay.
What we try and do is design the fuel system so they don't have. I've never heard that term before, pressure trap. But anytime you've got two positive shutoff devices and oil in between, when that oil heats up, you know, let's say that it's outdoors and heats up in the sun, you can generate an amazing amount of pressure in deadheaded oil. So there needs to be a relief valve in there. And you see those a lot in military projects, in hot locations where a lot of the piping is outdoors. But in most instances, you can eliminate the pressure traps by just making sure you don't have two positive shutoff devices in series. And really, there's very rarely call for that.
Yeah, I'm not sure how much the pressure you're going to be able to build against a foot valve. I've never thought about that before, but yeah, the only your escape from that would be to, if that's a problem, would be to reduce the pressure relief valve resistance. You know, that way it'll bleed off the excess pressure back into the return line, and you should be okay.
And if you build up pressure on one side of the pump's just going to coast a little bit and relieve that pressure. It's going to allow it to seep through. Now on boiler systems, I've had systems where we have a high oil pressure switch upstream of a safety shutoff valve, and then there must be a check valve upstream of that, and the oil can heat up just with, I've seen this on indoor jobs where the oil will heat up in the afternoon and trip your high oil pressure switch. So it doesn't take very much change in temperature when fuel is deadheaded to generate a decent amount of pressure. So if you do have a pressure trap like that, it needs a relief valve. And that's something we have to consider when we do the piping on oil-fired boilers as well.
Right. Next question is, and we're just going to do, there's some people that have left, and we might try to get to their questions via email. So we're going to do the ones that are people that are still here.
We've got a lot of diehards though.
Yeah, man, a lot of diehards. What's good. I'm glad these people are here.
It's the COVID.
It's the COVID, exactly. If fusible link valve closes on suction line of transfer pump, does transfer pump have low pressure switch, which in turn shuts down the transfer pump?
They don't. And
but the flow switch. Yeah, sorry, go ahead.
Yeah, the flow switch will trip the pump. Seems like most often, no, I guess we see them both ways, huh? But yeah, if the suction line is closed down, we're not going to shut down on high suction, but the flow switch should catch us.
You're going to have low discharge that'll shut the pump off.
Okay, great. Next question is, do you typically see a fire safety valve on fuel delivery systems for the generators? If so, where's the fusible link?
That's a great question.
I don't see them on generator systems that often.
Yeah, I was going to ask you if it's just a West Coast thing. Yeah, we don't use them a whole lot. We probably should use them. You know, it'd be nice if we use them more. But yeah, we don't use them a whole lot on the generator systems because they're required on the boiler side, right?
In certain jurisdictions.
Yeah, that's a good question. We probably don't see them. My answer would be I don't see them as often as I would like to, and I should probably try and fix that.
Well, you could put them inside the generator enclosure, and you could put them between the day tank and the engine pump, because the Model 110 gate valve, when it's open, it's almost like a full port valve, so there's not much pressure drop there.
Yeah.
And then if you get a fire inside the generator enclosure, you're going to quit feeding that fire more oil.
And they don't require any conduit or wire or any controls. They're just fully mechanical, so they're nice to have for sure.
All right. Next one is there special equipment to polish fuel for microbials, water, sediment, rust, etc.? How does one polish fuel?
So our filtration systems have their own pumps, and they have an upstream strainer that will filter out the large chunks and protect the motor. And then there's a downstream coalescing filter that spins the oil out of the fuel and has a filter element in there as well. And if we had our way, that filter element would be a 10 micron filter, but we can provide that with any filtration level you like. And you know, a 10 micron filter filters anything bigger than 10 microns. It doesn't care what it is.
You want to mention the DP switch?
Oh, and sorry. There's a DP gauge and there's a DP switch around each of those. So if you fill up the upstream strainer, or you fill up the downstream canister, an alarm goes off. And if you fill up the little water holding thing, there's a float switch in there that tells you, you know, you need to bring a bucket and dump that canister out as well.
We do make filtration units also that have auxiliary water recovery tanks and chemical metering as well. If you want to meter chemical additives automatically, we can do that as well.
Okay. Next question is, can you discuss the necessity of a desiccant type breather on tank vent piping?
A desiccant breather, I've never heard of that. I'm not sure what that would be for, to reduce condensation.
They're trying to keep down the moisture in the tank.
It's an interesting question.
I can't say that I've ever seen anyone specify that, but it's an idea worth looking at.
Yeah, I've never thought about a desiccant in the vent, but it's not a bad idea. I have
seen people put a nitrogen purge on top of the tank to keep humidity out of the tank.
Probably keep the air out of the tank too for a while.
Next question is, does your program stop fuel delivery on a leak detection, even if the life safety generator? So even if it's a life safety generator?
Yeah, so most of the time our systems are going to be programmed to stop adding fuel to a day tank if we detect a leak. But we have certain classes of customers that are extra paranoid, and I mean paranoid in a good way, that tell us, we don't care if we have a leak, sound an alarm, we'll get somebody to come look at the leak, but we're not going to shut down a generator over a leak. So it can be programmed either way. And
this is really the beauty of using a PLC-based system, is you can have sort of a logic tree that says, hey, if you know, especially at something like a first response hospital, it says, hey, I've got 2 tanks with 2 pumps each, 4 sumps. If sump 1 is flooded, move to sump, you know, tank 1, sump 1 is flooded, move to sump 2 on tank 1. If that one's flooded too, you know, check the others. If they're all flooded, then what are they flooded with? Discriminating leak detectors, water or oil? Well, if it's oil, maybe shut it down and move to another sump. If it's water and they're all flooded with water, none of them are flooded with oil, go ahead and run. So, I mean, and there are all sorts of layers to that, but that's the beauty of a PLC system is you can tell it if this, then that, and then deeper than that, if this, then that, if this, then that. So that's really what's great about the PLC system.
Great. Can Preferred provide a main control panel to tie components together from different manufacturers, i.e. tanks with sensors, submersible pumps, sensors, preferred day tanks, and flow manifolds?
So we can, and we can, we like to sell pump sets, but every once in a while we'll do a job with submersible pumps that are purchased with the tank, and our pump sets will control submersible pumps. We like to do, our approach to fuel systems is full service rather than self-service. We would like for everything in the fuel system that has a wire going to it to be provided by Preferred. And that way, we're going to guarantee that the system works, and we're going to guarantee that the system is programmed the right way. I mentioned earlier that the leak detectors on a Preferred system will always be made in the down position and then break in the up position. So if we detect a leak, a digital input goes cold. The float switches we put in a day tank are the same way. They're always going to be made in the down, not floating position. We did a job recently where a contractor supplied his own day tank and we supplied the pump controls, and the contractors could not get the system to work. Absolute full stop, everyone throwing up their hands. One of our guys went out to go take a look at it. He found that some of the floats were opposite, that they were made in the up position instead of made in the down position, and this absolutely baffled everybody on site, and they couldn't figure it out. And these float switches, if the operation is the opposite of what you need, you take out your little I forget the name of the little tool, but I went and bought one to take out the little spring clips, and you just put the little float on backwards, and now you change the action of, or you change the logic of the switch. So our guy was able to fix it right there with a snap ring tool. But what we see a lot of times, especially in Florida, and I don't know why, is that we'll see a Tremont day tank specified, we'll see a Preferred pump set specified, we'll see an Incon tank gauge specified. There'll be at least 6 different manufacturers in the fuel system. And when you do that, you're assuming that the contractor is going to make all this stuff work together. And that's a big assumption. So what we like to see is full service. Make us responsible for everything in the system that has a wire going to it, and we will make sure it works.
Great.
Next, I'll add one thing to that, and that is, for example, in the state of California, when we work on a UST system and we have vacuum monitoring, it's common practice for us to integrate with equipment from Veeder-Root or FE Petro and Con in order to do the vacuum monitoring. So we do regularly do it as well in those particular situations.
Well, Lee, we do vacuum monitoring now, and I know that we're working on getting all the approvals for it. Do we have the approvals to do that in California yet?
Not yet. They're in process, and as well as the PLLD that's required along with it. So that'll be AB 2481, compliance, LG 113 being the main thing, and we're also working on the PLLD aspect of it, which is going to be required. So.
Okay.
We'll see.
But I mean, LG 113 gets updated like once every 2 years, right?
I don't know that it's that often, but it's fairly well established now. I don't expect anything to, major to change. But yeah, we're just in the middle. You know, we've deployed that system elsewhere, the vacuum monitoring system, in other locations, and it's just particularly in California, we're waiting on California approval before we can deploy it. But
Gotcha.
yeah.
All right, next question is, someone's asking, do our fuel polisher systems sense or have a sensor that allows us to know, or allows the polishing system to know when it should polish the fuel? So, or is it just time-based?
It is just time-based. There's a 7-day timer kind of built into the controls. Now, that being said, you know, that's an interesting idea. VA hospital projects require water sensors in their main fuel tanks. You could tie that water sensor into the filtration system to run whenever that water sensor reads, you know, anything but zero. But I don't think we've done that before. And the VA hospital projects also, they always specify a fuel polisher, and my point has been that you really need one or the other. You need a fuel polisher or you need water detection. Having both is a little bit of overkill, because you shouldn't have any water in your tank if you run your polisher every once in a while. And I don't remember the last time I saw a water detector at a VA hospital with a preferred fuel system where the water detector wasn't showing zero. I think if you run your, you know, if you run your filtration system once a week, like we tell you to, the water level is going to be pretty close to zero in the bottom of the tank.
I could see some value to that if, for example, you got a delivery with a heavy concentration of, or for example, somebody left a sump cover off, and all of a sudden there was a big introduction of water into the system.
That's a really good point.
We could do that. I mean, we've got the technology pretty much to do it right now. If we used a magnetostrictive sensor with a separate water, you know, we can.
Which is what we do on VA hospital projects already. We could just tie that sensor into the filtration system.
Yeah. So yeah, I mean, we could do it right now. I think that Dave's point is, you know, 99% of the time is 100% accurate, but there may be an instance where it would be valuable to have that. Yeah, sure.
You know,
that's
both the pump controllers and the filtration controllers are both preferred FSC, so they could talk to each other via NodeNet just by running a 3-conductor belt in between the two. It wouldn't cost any money to do this. It would just be a change to the logic.
Yeah, that's what I'm saying. We can do it right now if that's something that somebody wants, and it's an interesting question. It's a good point.
I hope the person that asked that question hasn't already patented that idea.
The person's still on, so the answer is yes, I guess.
Yes.
The next question is, do you have a solution for dry fill lines in basements to rooftop remote fill systems?
We're laughing because we do something for that now, and Lee wants to do something better, and we've been kicking around his better idea within the company a whole bunch lately in the last couple of months. But the answer is yes, but we can't disclose how we do it because it's something we're trying to patent.
Fair enough.
We're working on it.
So I guess
in fact, let me say one additional thing on there. If anybody on this webinar is in the jurisdictional authority space, we would probably like to discuss it with you.
Yeah, because the last discussion with this is we've been talking with the other fuel oil people around the country, and we've come to the conclusion that it doesn't matter what they say so much as it matters. It matters what the code people, the fire marshal people want to see. You know, they're the ones that are driving this bus, and we need to do what they're asking us to do. So their
Yeah, they're
opinions
the reason
matter.
why we started looking at this. We weren't scratching our heads thinking of the next thing to do. Like, it's pretty much landed on us.
Yeah, so Lee's done a bunch of dry fill pipe projects in San Francisco. He has an idea for a better way to do it, and we're gonna file a patent on that probably before we release anything to the public.
All right. Very good.
We're working on it. That's the answer. Yes, we will have something for you soon. And I know who's asking the question now, I'm pretty sure. So,
I mean, we have something
yeah,
now.
we're working
Your
on it.
idea is a better way to do it.
Yeah.
Okay. So the answer is yes. So I think this is referring to the desiccant type breathers. The guy says des type breathers I've often seen on hydraulic oil pumps and systems that sell them. So I guess he sees those more in hydraulic oil pumps than pump sets.
I'm gonna check them out.
Okay. Someone says NFPA 31 talks about fire safety valves. NF 37 gen sets does not talk about fire safety valves. Okay. It's good to know because you guys referred that and the gen sets don't always require the fire safety valve. And that's it. Someone said, a bunch of people said thank you for the presentation. So gentlemen, I want to extend that to you guys. Thank you for the presentation today.
Yeah, well, thanks for coming and hanging in there.
This definitely sets a record for the longest presentation ever. And, you know, we're all sitting around with COVID and not having a whole lot to do. So, you know, back in the day, we used to do lunch and learns and provide lunch, and now it's a PowerPoint on your own TV, but you can provide your own lunch and because of the COVID.
Because of the COVID.
And I wanted to add one thing too. If anybody out there has a specific, like, hey, I want you to do a lunch and learn from my group, no problem, like we said, but also anything specific, like, hey, I want you to do a lunch and learn that's just about the controls aspects or something like that, definitely let us know, because we need to know, you know, if there are any particular topics that people want to drill down on or that sort of thing too, especially during COVID while everybody's around.
Right. Absolutely. For those that are still on, if you have any more questions, feel free to email David or Lee. David and Lee, I really appreciate your time and doing this. Well done. And any final comments, either of you guys, before we sign off?
Just thanks again for hanging in there.
Yeah, ditto that. All right, thanks for putting this on, Mike.
You're
and
welcome.
We had no technical difficulties after about the first 20 minutes, so woohoo.
Woohoo. That's it. All right, thanks everyone for joining us. If you haven't received your free copy of the Fuel Demystified, you can email me, David, or Lee, and we'll get one right out to you guys. And once again, appreciate you guys hanging in there. If anyone would like to review this webinar, we're going to be posting it on our YouTube channel in the next couple of days. Also with possibly some more information on what we're talking about here and some links in the description. So if you'd like to, you can view that. You can go to YouTube, just type in preferred utilities. Our YouTube channel comes right up there, and the webinar will be posted there in a couple of days. If anyone else has any questions, feel free to send them to David or myself. And I think that's it. Thank you all for coming.
Thanks, everybody.
Thanks. Bye.
Everybody.